So, were you guys able to implement Lagrange? Was anybody able to implement Lagrange? Yeah. Two, 3, 4, 5. Multiplication of two polynomials. What's rep? What rep did you use? Dense or sparse? Okay. I guess it's not a.
Not a number.
Oh, it's not a number. Are you using Rust?
Yeah.
Fine. No, you said let's do both. Were you able to do this? The first one I did was what? Was this one sparse? It was dense. Did you do sparse? Did you do interpolate? Were you able to do interpolation? Yeah.
And then I had a lot of questions in my head.
Do you know what the questions were?
Yeah, like at first, I was like, okay, before you can do the interpolation,
Yeah.
you need to find like you need to evaluate the polynomial at some particular point, and then you use the values you get, and then interpolate to get back the polynomial. But then another question was like, if you knew the polynomial at first, then
Mm.
why are you interpolating again to get back that same polynomial?
So in normal in zeta systems, you don't know the polynomial, but you know the points. So what you know first is not the polynomial. It's just because you know you are doing tests. So you have to think of a polynomial first to get points. But in normal systems, you know the points first.
Okay, so it's not possible that I just pick random numbers. I need to actually have have a polynomial, evaluate it, get the results.
The reason why you need that is because you're testing,
Yeah,
alright? So if you just pick random numbers and you do your interpolation, how would you know if
exactly. How do you
that's the
know
correct
that's the correct?
polynomial? Yeah. So just for the test. That's why you need to know.
That's for the
Yeah.
polynomial.
Just for the test.
Yeah, I think regarding the interpolation thing, I have kind of like a logical, will I say, what's it called, argument or something that implementing, like, would the interpolation be a function inside the implementation of the polynomial struct? Because I feel like, because when I was discussing with my roommates, that if if the goal is to find a polynomial and the polynomial doesn't exist yet, so putting the interpolation in, like,
The polynomial
yes, that
struct.
means you already have an existing polynomial that you now want to call interpolate on. Meanwhile, the interpolate is supposed to like get that polynomial.
Yeah, but you know in Rust you can have methods that are not linked to the state. So just don't put self. And then when you do so it's all about choice, right? You could decide to have like an interpolate outside of polynomial
Yeah, that's
entirely.
how I did it.
Yeah, that works also.
Yeah, but what's the other way?
You just put the function in there, but then you don't put self. I'm coming. Let me just. You guys won't be able to see it. It's too big on my screen. Okay, so you have a struct, right? Let's have a struct. My U is not working. I'm pressing U and it's not working. What's going on? But it's working now. But I was not though. That's why I wrote it has gone again. It's almost as large as it can be. Oh. Okay, wait. I'll try. I'm hoping that it's because of this thing. I hope it's because of this thing. Okay. So Okay. So you could do something like this, right? You can't see. Um, is it better? You sure? Okay. So see, the function is inside the implement block, right? But then there's no self there. So what this means is that you can call it directly from the struct. I don't get. You don't need to instantiate a new. So normally if you have something like evaluate, right, that takes self and maybe returns something random. I'm just not going to return anything. Now in this case, because there's self, it means that you need to instantiate first. Then you now call the method on the instantiated object. So this is now like Univariate poly dot dot. So you have to create a new one. I'm just going to just right. Now you can now call a dot. So this one requires the existence, but this other one doesn't require.
Now it's like you're calling the method directly on the class.
Exactly, directly on the class. So they have. It all depends on your style, whatever you want to. Whatever you want to achieve. Alright. So, did anyone have questions while trying to implement that you want us to go over? You want us to implement?
Yeah.
Especially interpolate. I don't know how to implement interpolate. But this is the only one we're going to do a walkthrough like this. This one is just so that anything that you see that is new, let's say from a Ross perspective, you can just ask, right? But then further ones, we're not going to do like a walkthrough like this. I don't think we're going to. Right? It's now going to be more pointed. Okay, they're going. So that I can compile. So like right now, I don't know why my U didn't work here. Oh. This is so weird. I'm coming. Yeah, but why isn't it? Yeah. So there's not really comments though. It's more like it's a placeholder for I will write something here later, but it will make the compiler not shout. Yes. Yes. No, to do. To do, yes. It's to do. So this will still compile. Like, I think I can do cargo build now, and it still works, right? Even though I'm supposed to return self here, but I'm not actually returning anything. But if I remove this to do now, and I compile, you can see that it's saying that I said I was going to return self, but I didn't return anything. So to do is like compiler is like, okay, I won't check what is inside, but if your code reaches there, I'll throw an error. So if I call interpolate, let's say in a test, then it's going to shout. Well, there's no need to do that now. So there are multiple ways to do this. We right now want to keep states, right? We want to keep the representation of our polynomial in memory, right? So we could decide to put that in a struct, or we could decide to have ephemeral states. So I think some people just use like their entire polynomial is just an array, right? It's not a struct per se. So they just have methods that you call, you now pass the array in there, yes, and then they know what to do with that. But you can also just use like a struct representation. I think I prefer the struct representation, so I'll probably just use that. So now it's a decision of whether dense or sparse. So I don't know. You guys have to help me a lot here. It's not coefficients now. Okay, let's see. What are we trying to put here? We're trying to be able to represent any Should we use fields? Hmm? That's fine. So we have a vec, alright, of, I don't want to use pass. Why F64?
Yeah, the floating point.
That's like for interpolate, right?
Yeah.
We'll soon use fields. I don't like real numbers. Well, it's fine. Okay. And then you can also do something called generic, right? Where technically your polynomial could have been over F64, it could have been over U32, it could have been over anything, right? So you could have a generic type here, T, and then this is now replaced with T. So what this does is that you're telling the univariate polynomial that I don't know the exact type I'm going to instantiate you with, but I'll pass it when I call you. So this is an example of how you might now instantiate it. Right? So you can now put the exact type you want. So let's say you want F64. And then does it make sense? Then another example you might use like a field elements, another example you might use. But I'm going to be specific man, because I think F64 is probably the. So any questions you have as we go about this, please just ask. Okay, so now this is supposed to represent what? Coefficients, right? So I have one for each power of x. Yeah? So what's next? What else supposed to implement? Degree? Is it glitching again? Okay. So the degree needs to have the state, right? You can't find a degree without knowing what the polynomial is. So that's why I need to take self. Now you could do self. This is a borrow. So borrow is more like I don't need the data. I don't need to own the data, right? There's something called ownership in Rust. So you need to know who owns what. So this state now, in order for me to get the degree, I can borrow the data, just look at what I need to look at, and then return it back to you, right? So that's where you use this reference, right? Then there are other cases where you're like, I want to borrow data and I want to change things about the data. So that one is now like, imagine if you wanted to do like, you wanted to store the degree here so that you don't have to complete it every single time. What you could do is that you could have the degree in here. You can have the degree in here as like an option of, let's say, U size, right? So you have the degree here as an option of U size. Then that means that when you compute the degree the first time, you will now save the results in here. Now when you are modifying states, and because of that, you need to borrow mutably. That's like you need to borrow in such a way that you can mutate it when you are done. So that's what you use in this case. I don't see it as necessary per se. So I don't feel like we're calling degree a shit ton of times, so it doesn't really. So what you do here is you solve the coefficients .len minus 1, right? And then you return that as the degree. Makes sense so far? So degree is easy. Then is it prayer or Okay, so next thing is evaluate. So to evaluate, we also need the states, but we can borrow the states also. We don't need to take the full states here. So also self, and then we need the points that we want to evaluate at, which is going to be x. What's x is for also? Oh, okay. Then we're going to be returning f64 as our evaluation type. So if we're using generic, I think I should use generic just so that it is. I can show you how you would have done this. So if we're using generic, you do this. I'm going to change it back to s4, but I just want to show how one would have done this. So x is going to have to be the same type as the coefficients, and it's going to return the same type as the coefficients. So this is how you use generic to represent this same structure. So now you can replace it with f64, a field element, any random field element, it doesn't matter, but they are all generic. Okay. So now evaluate. How do we do this? So we want to go over each coefficient, right? And we want to raise x to the power of the current index. Then multiply that with that coefficient. And at the end of the day, sum up everything. There's a way to do this like with for loops and everything. But Rust, you usually want to use like iterators. You are describing data flow rather than just like doing it directly. So I don't know, should I do both or let me just okay, let's do both. Okay. So if you want to do both, what you need to do now is like create a for loop that goes over the entire coefficient array, right? So you can do for I in 0 dot dot self dot length. Self dot coefficients or length. Right? So now this is going to give me the index of every point in the array. Cool? So once I have this index, I can now raise the power of x. I can now raise x to that power and multiply it by the coefficient at that particular location. So the coefficient at the current location will be self dot coefficient bracket I, right? So if I is 0, it will give me the first coefficient. If I is 1, it's giving me the second coefficient, and on like that. So I'm supposed to multiply this by x to that power, right? So I'm going to do x. Is it the power? Power f, okay. Power f what? I. Does this make sense? So why is this complaining? I is use size, okay. So there are types, right, that you can convert to another type easily. So if the type is bigger than the type, like let's say you're starting with U8. U8 is small. It's just 8 bits. And then you're going to U32. It is safe to convert from U8 to U32 because of you're not losing any information. U32 was already big enough. So you're just going to add zeros to make it long, right? But then if you're going from U32 to U8, now that is dangerous, right? Because of your U32 might have more information than a U8 can contain. So Rust is now like, how am I supposed to know you're not doing something bad, right? So that's why sometimes you have to like try into in order to convert it down. But if you know like Rust can only reason about like syntax and what it can see. But you as a programmer, you know the domain that you're working with, right? So let's say we know now that the U32 can never be bigger than the U8. Like we know from the domain of the program that we're working in that U32 can never be bigger than U8. We're just using something big to hold something small, and it's always going to be small. Then it is safe from your program logic perspective to do the try into and force it down to a U8. But now x64 is bigger than U size, right? It's like U size plus some extra stuff for like decimal. So it's safe to convert it. And that's why I'm able to just do it like directly. Okay, so now we have this computation. So now we are able to compute the coefficient times x to the power for every power. But now we need to sum that result, right? So what we could do here is we could create a new variable. It has to be mutable so that we can add to it. So let's say the evaluation, let's say evaluation is equal to 0.0, right? Since we're working with F64 here. So what we'll do now is do evaluation plus equals this, and then we'll just return the evaluation. So this is one way to do it. This is the normal, the iterative way. It's okay. This one is okay too. Like, it's fine. It's just that once you start writing Rust a lot, you start to prefer the other. So does this make sense? Okay.
So this is exact point. If you are using, let's say descending degree, because they are using ascending degree. So if you're using a descending degree, at this evaluation point, you would have to change your index.
Yes, you have to change. Yeah, you have to change it here, in this place, right? Yes, this place here. So what it's saying now is that, right now our coefficients are like this. X raised to the power of 0 is here, then x raised to the power of 1 is here, x raised to the power of 2 is here, on and on, up to x raised to the power of n, right? But this is also equivalent to the index, right? This is index 0, this is index 1, this is index 2, up to index n. So we're able to just use I directly as the power, because that corresponds, right? This is I technically. So I is this, and I corresponds with the power. But then there's another way you could represent your coefficients. You didn't need to represent it x raised to the power of 0 first, right? What you could have done is you could have done x raised to the power of n will be at this side, right? Then x raised to the power of n minus 1, then x raised to the power of n minus 2, all the way to x raised to the power of 0. So 0 now will be at the end. But I is non-changing, right? So now you need a way to go from 0 to n. With the n, n is the length, so it's going to be n minus 1 by default. Sorry. I didn't even get what just happened. Since it's 0 index, it's not going to be let me just make everything right? So we need a way to go from 0, because we won't be able to just use I here, right? Because the coefficient that is here is supposed to be raised to the power of n minus 1, not to the power of 0. So we need a way to go from 0 to n minus 1, right? And you can just say that n is the length of the array, then 0 is the index. So you can just say that, okay, the mapping will be like, whatever your I is, just do n minus I minus 1, or n minus 1 minus I, anyone, right? So this mapping now is sufficient to do this transcription, and we can show this, right? So that's why we had 0. It's now be n minus what? 0 minus 1, right? Which will be n minus 1. So you can see that 0 and n minus 1 have been found. Then if we had 1, it will be n minus 1 minus 1, right? Which is what? N minus 2. So you can see that it is able to figure out what the so now if it was n, let's say we had the last one, which we're expecting to be which one? This line? I don't know where there is 911, okay. Which n? This one? Yeah, you're right. You're right. Okay. So this is n minus 1, because it's 0 index, so we're not going all the way to n, we're going to n minus 1. So if it was the last one, that would be what? So now this is the index, right? This is what I was going to be. So we'll just put in this formula, n minus what? N minus I. I is what? N minus 1, then minus 1, right? And then we do this, so this is n minus n plus 1 minus 1, right? So we're going to be able to get rid of the n's. N minus n, that's going to be 0. So we're going to be left with 1 minus 1, which is also 0. So it's able to do the mapping, right? So you can choose the order that you want, and then as long as you can figure out the relationship, you are good. That's why I was like, your representation is up to you. So there might be cases where maybe this order is better for whatever reason. You just do that. So, but for us now, we're using this direct order. This one that the index corresponds with the power. So that's fine. That's fine for our case. Now I'll show you the other way you could do this evaluate without having the for loop and all. Okay. So there's a different way to look at this thing as like data flow. So data is flowing from one source to another source. During the flow, there might be transformations. Okay, you might do some transformations as you are moving this data. So I'm just going to use the Rust playground so that we can test it out quickly. Yeah, you have a question.
If that struct was outside that file,
Yeah,
are we still going to be using self when we're implementing it?
yeah. As long as, so regardless of where the struct is, you'll still have this thing here, right? Are you seeing my screen?
Yes.
You still have implement with the struct name.
Yeah.
So as long as you have implement with the struct name, self just refers to whatever is here, right? It doesn't care about this. It doesn't care about this, right? Self is whatever is here.
So in the later programs, anytime we refer to self, we're talking about that.
It's just that what we're talking about is also in the same file, right? But you could have had your implement block across multiple files, but still the same structure. So you can see yourself. Does that make sense? So self is just this. Good? So now data flow. So there's something called an iterator in Rust, which is a way to take one by one from some source, right? So you have a source. The source in our case would be the array, right? So we have an array of numbers. So you can use your iterator to take one element at a time from the source, right? And then you can pass it on to something else. So you can do this kind of chaining where you can now do like some interesting stuff. So right? So we have a vector now. This is going to be our source. But we want to now make it an iterator. So the way we make it an iterator is by, let's say we can call it a iter or something. It doesn't really matter. So there are multiple ways to make things iterators. So there's into iter. What into iter will do is that it will own a, right? So it will consume a. It's saying that I'm a source. As I'm passing information, I'm destroying it at the other side. That's what into iter is doing. So once this iterator is done, that a does not exist anymore. It has been destroyed. You get? So this is like it's swallowing the data and it's doing whatever it wants to do with it. So whenever you have data that you only want to use once, you can use something like this. But when you have data that you still want to keep, but you still want to do this iteration, you will now use something called just iter, right? So now instead of consuming the information, it's just like passing you it's borrowing you the data, right? It's just going to borrow it to you. So what's the best way to visualize this? Okay, I can now do something like I'll print out the first thing that the iter will give me. So a.iter.next. Okay. So next is how you ask the iterator for the next item. So in this case now, the next item is going to be I was supposed to use what I created. Now I created a underscore iter, and I'll call a.iter again. So I was supposed to use a underscore iter. Yes. No? No, sorry. The iter itself is mutable. I don't know. Let me try and explain that. So the iterator, every time it asks you for something, it has to keep track of the last thing it has given you. So this means that every time you ask for something, it needs to change itself a bit. And you can only change yourself if you are mutable in Rust. So that's why the iter itself has to be mutable. Does that make sense? So now it has seen that, okay, I've given one thing out. I have so and so left. So it changed itself in that case. So look at what it gave me now. It gave me 1, which is the first element in that list. Does that make sense? Then I can now do this again. So I can say, give me the next one. So it's going to give me 1 and 2. Yeah. Oh, DBG is a way to print, but without. So you know, if I wanted to use print line, right? That's the one you know, right? I will need to put this and then now do a the next, which is annoying. Okay. So like, see this now. It can't be formatted with just regular prints. So I have to use debug print, which is like the and then now I see it. But it's cleaner though. I like this way this one prints it out. Right? Like see, it's just this. The other one has to now put like debug information and everything. So what this other one does, this DBG does exactly what this does when you put this dot this. So it just does this. But this is cleaner, I won't lie. So I'll use this one. I'll use this one now. So now we're going to have 1, 2, and 3, right? So the sum now is because of, you might keep calling from the source and there's nothing left. So then it's returned to none. So we're going to do it again. This is the last one. 1, 2, 3, 4. Alright? And then if we do it again, we're not going to get anything. We're not supposed to get anything. So we're going to get none. So that's how you know that the source has finished giving you what you need. But then I'm supposed to be able to still print. Sorry, I have to use DBG for that one. So you can see that I can still print A after I'm done. So I'm showing you now the difference between iter and into iter, right? I can still print A after I'm done because it was just borrowed. A still has the data. So that, but if I did into iter instead of iter, all of this will still work, right? Except for the, so I'll still see 1, 2, 3, 4 none. But then when I try to print A, you get a compile error now because it has been moved away. Yeah.
Like in what situation
Do you use
actually, like, how would you say which one is best to do it? Is it into it?
so if you are not using the data more than once, just use into iter.
Does that have any advantage?
Okay, does it have any advantage? Well,
Has there been any use case? Have you had any use case for it?
yeah, I use it all the time, but it's just mostly because of I want to destroy the data immediately I'm done with it. Like, I don't want it to linger in memory at all. So like exactly like saving space. But that's not, it's not a concrete, very concrete reason like that. But this makes sense, right? So now we have something that can give us the content of our array one by one. So we can do certain things with this. The next thing we can do is we can not just get the content, but we can also get the index, right? So there's now a pipe. Let me go back to iter, right? So you could do iter, then you can now, there's now another, this thing, there's another, so you know, the data flowed from the array to this iter. Iter is now saying, okay, I'll give you one by one. So there's now another stream or something, but it has functionality in it now. Anytime it sees data, it's keeping track of the number of things it has seen, right? So that's how it can assign an index to each of them. So I can do the enumerate. That's what does that, right? So now if we do exactly what we did again, we now see that it's not just giving us the data, it's also giving us the index, right? So this enumerate is like a pipe on its own, but it has someone sitting on top that is counting, okay, this is the first thing I've seen, I'll give you index 0. This is the second thing I've seen, I'll give you index 1, right? And then that's what enumerate does. And we know we need this because we need the power of x, yes. So that's where we'll get the power of x. It's the first element in the tuple. while the second one is the coefficient. Make sense?
Yes.
Okay. Now there's something called a map, right? So a map is now like, it's also like that, but it's like, give me something and tell me what you want to do with that thing. I will do it for you, and then I will return what the answer is supposed to be. So let's say I wanted to multiply every number in the array by 2, right? That's functionality that, let's remove this enumerate now. And I want to multiply every number by 2. So I will do map, right? Map takes a closure. A closure is basically a nameless function, right? So this is the where you put the function arguments, and then you have the function's body, right? So the map is going to take what is coming from the previous source. In this case, that's just eta, which is like the array, right? So we're going to call that, I'm just going to call that value, right? Then I can do whatever I want to do with this value inside of this body. In this case, I'm just going to say value times 2, right? So now it's just going to multiply every single element by 2. And now, when I call eta.next, I'm not expecting 1 anymore. I'm expecting 2, 4, 6, and 8.
Sorry, so the map takes in the value
Yeah.
and then uses the value to perform the next one.
Yes, that you defined. So you define the operation that you want. So you can see now 2, 4, 6, 8. So this is what we're going to use for our evaluation. That coefficient times x raised to the power of something, because it allows us to do any arbitrary computation, right? Then there are things called reducers that basically take a stream and then compresses it into just like one thing, right? There are lots of them, but the one that we care about right now is just sum, right? So there's something called the sum. So what the sum will do is that it will take the source and it will add it. So it's just add everything that it sees so far. There's dot prod, I think, which does the same thing but for multiplication. So it takes the stream and then just multiplies everything. So this means that when we are done with this, it's no longer an eta. It's not just going to be one item because it has been. So I'm just going to stop printing this and then just print the a eta dot sum. So this one now, it doesn't know the type, and that's why it's complaining. It needs to know what type I'm using. Where's my print? Okay, 10. Is that correct? That doesn't make sense, right? Are you sure?
Yes.
How?
No. It didn't.
Actually,
It didn't map. I think.
Because you see,
A
I made a
underscore
mistake
A.
again, yeah. I did a dot eta, so it's going back to this one. So I'm supposed to do a underscore eta. So then to add the 2, 4, 6, and 8. Does that make sense? So it's not a function. So now we have 20, which makes sense because we multiply it by 2. Does that make sense? Okay. Now let's use this to now implement evaluate. So evaluate is basically going to be, we want to loop over the coefficients. That's like the coefficients will be a source. Then we need the index for each coefficient, right? So we're going to say self.coefficients. We don't want to collect the entire coefficient state, so we're not going to use into eta. We'll just use eta. So the eta. Now we basically have each coefficient as a string, so 1, 1, 1, 1. But we need the index also, right? So that's why we do the enumerate. So enumerate to give us each coefficient along with the index. So the index will be first, then the coefficient, index, coefficient, index, coefficient. Then the next step will be to now do something with this index coefficient pair. So like that's the only information we need to be able to compute like each monomial term, right? So we use map, right? So map is going to pass whatever the last source will output and you know it's going to be outputting a tuple. So this means that we're expecting a tuple. So the first one is going to be the index, which you can call I, and next one is going to be the coefficient, right? So now we can do the monomial computation, right? So what we could do now is we could say coefficient times x dot power f I as f64. So this would now do the computation, and then finally we can just do dot sum. So this means that we can get rid of all of this. All right.
I know reference to that question.
Is that?
Question.
Yeah.
I know reference to it.
Yeah. No, you mean like I should destructure it?
No, the other one, yeah.
Yeah. It's a reference. So the reason why the reference because it's eta, right? You know it was borrowed.
I thought you were going to put like the and before the coefficient.
What and? Here?
Ampersand, yeah.
No. There's no need. So the type is already referenced to f64. This is just a variable, right? Just a variable. Let me check if it compiles. So it does compile. I don't trust the IDs. I don't know why. I have to check the compiler. So this works. This should work technically. Let's write some tests. Does anybody have a dense poly? What's the actual poly definition? That's the equation from
1 plus 2x plus 3x squared.
1 plus 2x plus 3x squared.
Yeah.
Okay. So this means that we are. So I'm just creating a function that can return a particular univariate poly. So So since you know x raised to the power of 0 is the one at the first entry, so that will be 1. Then x raised to the power of 1 is 2, and then the other one is 3. But I need to use floats. This is why I hate floats in Rust. Rust is sometimes so dumb. So this is so obvious. It's so obvious that this is f64. I don't need to put dot 0.0. So this makes sense, right? So this is now like a polynomial that we can use to do like tests and stuff. So let's say the degree, for example.
Sorry, I didn't interrupt you. I was planning that it is better now. That's
Yeah.
Yeah.
Phone. After. Later. Okay, guys. So the degree is supposed to be 2, right? So if I do poly1 dot degree, I'm expecting 2. So if we cargo test, so that one passes, right? Now we should just test evaluate. So no, evaluate. Let's say I want to evaluate at 2, right? What's it going to be?
17.
Okay. So we chose the same number. So what I like to do, just to make sure this is not deceiving, I like to sometimes make it fail, just so that I know that okay, it's working. Alright. So evaluation works, and both of them should work, right? Like if we uncomment this and we comment this, we should get the same. Both of them are passing, right? So you could do it any way you want. It's just not a matter of like style.
Is there a difference like say speed of competition or something like that?
Yeah, both of them are. I think both of them are slow. Both of them are slow. There's redundant information about. So there's a redundant computation. Like see now, x raised to the power of 0, right? I did it first. Then I did x raised to the power of 1, which is just x. Then I did x raised to the power of 2. So what did I do? I did x times x, right? Then I did x raised to the power of 3. I did x times x times x. But if you look at x raised to the power of 3, x raised to the power of 3 is x raised to the power of 2 times just 1x. So that means that when I'm computing x raised to the power of 3, I don't need to start from scratch. I can use my previous result and just multiply by x once to get the next power of x. Then for x times 4, x raised to the power of 4, I don't need to multiply x by itself 4 times. Just use the previous result and multiply by x once, right? So that way you're going to be, I don't know, technically it's so small, but if you have like a really big polynomial now, that's where you start to see the differences in. So all of this right now is just slow. All of this is slow.
So how do we do that?
How do we do that? Okay, let's see. Let's refer to it in this. Should we bench? I'm going to bench. I'm coming. So now, instead of power of this, you could do like, let mute current x or something, right? Equal to, 1, right? Because x to the power 0 is going to be 1, right? So that's like 1.0. So that's f64. So when you are doing this, your computation, you're going to do coefficient times current x, right? So the first time you're going to run it will be x to the power of 0, which will be 1. So that's fine. But then next time you want to run it, you need to have updated x, right? So the next time you want it to be x. So what we'll just do current x times equals x, right? And now, next time x is going to be 1 times x, then x times x. So this is faster than what we had previously, just because we're not repeating redundant communication. So let's just check that it still passes the test. So it still passes the test. So this works. How you do this with the pipe, I don't know yet, but we'll figure it out. Yeah? Understand? Okay. Take on to the last question. So let's see, how do we do this with the pipe?
But is there a way to check for speed or just?
There's a way to check for speed. You have to set up benchmarks, but it's too much of a hassle right now. So there's something called criterion. So you can use this to set up benchmarks. Let me use the crates. It's supposed to be a quick guide. Yeah, so see now. So they have this function called Fibonacci, right? That they want to test the speed of. So what they do is they have this like seed of bench. So it's trying to bench Fibonacci on 20. So to find the 20th Fibonacci number. And then you just write your code like this basically. So you put the thing you're trying to bench inside of this, right? And then at the end of the day, you're not going to have a result that looks something like this. So this is telling you the time it took. In this case, this is like 26 microseconds, right, to do Fibonacci 20. So it's going to run it a ton of times just to get the average. Because that's the problem with performance. It's more of an art than a science per se, because your computer might be faster. There's a lot of noise. There's a lot of noise in measurements. So you might run something now and it's fast. You might run something 10 seconds later and it's not as fast. Or it's way faster, the same thing. The exact same thing. Yeah.
What about since you're working with arrays, right? Since it's an array, what about like a particular search algorithm that will actually make it faster? Going through sorting the array.
What are we searching for?
Since we are searching for the numbers, I guess, because we are implementing arrays, right? In case we are working with arrays, generally. So, what if there's a better algorithm to like go through those arrays? Don't you make the stuff run faster?
Yeah, that's only if you are looking for something in the array, right?
Okay.
But in our case, we're touching everything in the array, right?
In the line of touching, we are still going through.
Yeah, but we're going through because how do I put it? We're not excluding some things, right? We're not saying that, oh, I want just this and this and this, right? We're saying we want everything, and the fastest way to go through everything is to just go through everything. You get? So there's no need for any complicated algorithm that you go to the first one, go to the last one, go to the middle one, and you still touch everything. In fact, that is slower based on how CPUs work. There's something called like a cache line, like internally, and what is fastest is predictable access patterns. So like if the hardware can predict what you want next, it can load it for you before you even ask for it. So if you are jumping around, it's random, right? The computer cannot know what you want next. But if you are going first, second, third, fourth, fifth, it's like, okay, there's a pattern here. Let me load 6, 7, 8 for this person before they get there. And it will be way faster. That's for this, because we're touching everything. If you're looking for something in an array, then you cannot say, okay, let me do binary search, right? You break it half, and then now we are looking for something specific. In fact, binary search is slower than just going through everything. For small array sizes, it is slower. Technically, going through everything is
like reducing the time complexity now.
That's all over the end also.
Yes.
no, going through everything is O of n, right?
Yeah.
Doing binary search is log n,
Yeah.
which is much better than n. But because of how CPUs work right now, before you hit that point where that log n is better than n, you must be doing something really large. So that's why this thing is not, you don't guess it, you have to measure. You do whatever you do and you measure. If you see that it's not as fast as you expect it to be, you find something else. Then you measure again. You see, is this better than what I had? If it is, why? All those it's like an experiment. They're just like trying to optimize the performance of things. But binary search, because of it's not predictable, right? The computer cannot know where you're going to go next. Because you have this if statement that you're like, if what I found is greater than what I was looking for, I should go to the left or I should go to the right? That's not predictable. The computer cannot know beforehand. So the computer cannot do anything for you. So, but if you're going through everything, then the computer can be like, okay, let me help you load. And it's so crazy now that like, there was a matrix, I don't know how to put it, like let's say you have a matrix. You can iterate over the matrix. That's like you want to just print out everything in the matrix. There are two ways you can do it. You can print it out row by row, and you can print it out column by column. We did it. The only difference between the two algorithms was just we switch I and J. That was the only difference. 2 for loops, the only thing we did was we switch I and J. One of them, I can't remember the exact numbers, but Francis, it was like, one was like 190 or so, and one was like 10. Like it was like 19x slower. 19 times slower than the other one. And the only thing we changed were 2 characters. That was the only thing we changed. And that's because of the computer prefers the row by row. Because in memory, the first row, they're all together. Then the next row, all together. So if you start accessing from this front, it will know that, oh, okay, let me just load the things that are side by side. So you can just go fast. But then if you're not doing like this, when you come here, it will load everything here for you. But then you said, I don't need this one. I'm throwing it away. Then you now came down. It's now load everything here for you. You said, I don't need it. You now went there again. And then this loading and throwing away is really expensive. Like if you look at cache lines, there's something called cache lines. If you look into cache lines, you will see what I'm talking about. So understanding how like the CPU itself works is really important for understanding performance. And big O is not enough. It's not enough anymore. It was enough before, but it's not enough anymore.
We have a GPU, dedicated GPU, we need to go faster.
You have to also understand how the GPU works and trigger your algorithm to take advantage of that. So the key is just understanding. Okay, so now let's look at this thing. Is there a way to do this? With a pipe. So we don't want to enumerate again, right? There's a way to do it with fold, I think. we're trying to do this faster method
With the what?
with the pipe system.
Pipe.
That's iter, enumerate.
Okay.
You get what I mean? Then we can fold it. What's that? Yeah. I'm thinking we sum it and we accumulate. I'm coming, let me just try this out. So solve the equation the iter, right? Which will give us 1 by 1, right? Then we can now do, I think the fold. I've forgotten the function signature for fold.
That's in the initial value and the accumulator.
But what will be the initial value? I'm guessing that will be the sum, right? But I also need x to be flying around.
I think going this way now would be like that's the same thing.
Yes. I'm trying to do the distributive approach.
Especially with the constant.
Yes. Which is 1.
Yeah. No, see,
I get what you mean.
the constant of polynomial
That's, I mean, so I've already like gone next once.
like that now depends on the orientation. For the dense type, that should be the
Index 1.
guy index one.
So like let's constants.
But for the sparse type, that's going to be
That number will be this.
no, the pay, guys, it's going to be paid.
Oh,
Because we need to find
So 4 takes the init and then it takes the closure. So in this case, what's the init? The first element. Then we have the closure. The closure is taking what? The accumulator and the... Right? So, and the accumulator is based on what? The constants on. Initially, I guess. So what we want to do is we want to be multiplying x. Yeah?
this eta dot net is a little bit confusing for me.
Okay.
That I was thinking like if you have like the previous array we had, like
Yeah.
1, 2, 3, 4.
Yeah.
I think when you say next,
Yeah.
it should be 2, not 1. But this one, even though you say eta dot next, it starts printing from that one and then 2. So
Yeah, eta dot next will always give you the first thing. If that's the first time you're calling it, to give you the first thing.
So what's now the next? I thought the next was like giving the next value after this also.
So the initial value will be nothing. It will be like at the beginning of, let's say at the beginning of the line. This is where it will be. Then when you say next, it's to give you E. Then when you say next, to give you V. Right? I think you're assuming that it is here already. Yeah, no, it's here. Right? So now what do we do?
so
We have this distributive, there's a distributive property that we're trying to take advantage of. So the accumulator is the constant, and then we're supposed to do accumulator plus, I feel like we need to write out this.
like accumulator plus the next
Current.
yeah, plus current times x. All times x.
You need to like accumulator equals to like accumulator.
Wait, let's try and write it down first. I'm coming. So this is what we have, right? We have what? X. That's a C1, right? Then plus C2 times X. C2 times X plus C3 times X square, right? Plus C4 times X cubed. On and on like that. Now we're trying to get rid of the repetition. Alright? So we can remove this. We're factorizing out x somehow. So let's just factorize it from this one. Right? Let's remove this first. Let's see if we can do this reduction. But then C1 is, well, it's supposed to be C1 plus brackets, right? Then x into C2 plus C3x. This is, so it's always the accumulator plus x times, but does this mean that we need to reverse it and start from here? So we do C3 times x first, then we add C2 and multiply everything by x. Do you get? So we'll do the rev. So the rev is like another way to, it reverses it here. So now this is going to be the last, like the last coefficient. Alright? So that's going to be like the first thing we do. So what we're supposed to do now is, let me just make sure it works first. Then we'll see how I can explain it. So it's last coefficient of the accumulator plus the current all times x. I think it should work, I'm not sure. Yeah, I'm coming. Let me just make sure it works first. It's double. Yeah, you want this one?
Yeah. So remember what you said last about how CPUs work and all that, my appreciation. This one, aren't we doing a lot more things than what we're doing before?
Which one?
Like this,
Oh, you mean like relative to this?
Yeah, trying to optimize this.
Probably because I've not gotten it yet. So once I get it, I'll know whether it's less or more. But it's not supposed to be less. There's just a bug here.
I think it will just be accumulator plus current times x.
It's just current times x. Why? Because this is here like this, right? This is equivalent to this, isn't it?
Yes.
Current is what?
Current is like the next value in the array.
Yeah.
C2, C1.
But let's try it though. But I don't know. Times x makes sense here now. Right. Because it's the last one, you took it out.
I'm not supposed to tell you. I found multiplication of 13.
Which one?
It's the one I'm 13.
What I'm thinking is supposed to be there is because of, I think the problem right here is because of this C1. I'm multiplying it by x when we're not supposed to. No, there's always a times x here. That's probably the problem.
What if we remove the first times x?
This one. I'm thinking that the times x is supposed to come after. That's like in the next round. And if it's coming after in the next round, that means that this is going to be the accumulator. So it's the accumulator that was supposed to multiply by x. And then we add it to the current. Then the next one will now, that's it. So that means we don't need to do it at the top anymore. So that's it. I don't know how to explain this. I don't know how to explain this. So
You're going to share the code with us.
I hope, I'll try. I'll send it. So how do we do this? But is there no way to remove this unwrap? There's something called reduce now. Reduce is different from fold. I'm coming. First reduce unlocks. I think reduce allows you to take the first element, but without an initial value. Function returns none if the iterator is empty. Yeah, reduce is what I need. I just hope this works. What am I supposed to do here? I found. Put it down. This one? Let me see if this works. You return an option. I just unwrap. That wasn't a problem. That was a problem. This person is a reference. All you know require mute. Okay, let me look at the function signature of reduce again. This is a crate. I'm trying to simplify it first. Item and returns item. So it doesn't want to do any reference. And right now we're doing the iter, which we need to. Can I do the cloned? Then I won't need okay, it works now. Okay.
So, quick question. Is iter not a keyword?
Is it not a
It's not a keyword.
keyword?
Like, what are you, the way you're using it is iter not a keyword?
Did you say keyword?
Like ITER.
Yeah.
It's not a keyword.
A keyword. I'm not hearing. Did you say keyword?
Yeah,
Yeah. It's a keyword, but as a function, not as a.
That's a variable.
Yeah, if it's as a variable. But the keyword as a function, not as a. Rust is smart. Okay.
So you can use it as a variable name.
Yeah. Okay, so this is the final thing.
But you can't use it as a function name.
I don't know. Let me check. not complain. You're
Would
welcome.
that not be a compensation for you as
I think you will need
if
to
you have it?
specifically import it wherever you want to use it. Yeah. So it's succinct now. It's actually succinct. Like it's not crazy. It doesn't look like a lot of work.
So they have to relocate. But we know what it is.
Okay, so the idea was we didn't want to do, this is like C1, this is a constant, right? This is x raised to the power of 0. Then plus C2 x raised to the power of 1, right? Then plus C3 x raised to the power of 2. The problem with this was that we're always doing the full multiplication every single time, right? So here we'll do x raised to the x times x, then x times x times x. So we wanted to save that computation. So there's a way to mathematically save that computation by factorization. So this is how it's done. So you factorize, since there's x here and there's x here, we can remove that x, right? So then there's C2 and just C3x. So how many multiplications were here? Let's now like count the amount of multiplications. So here it was x times x, right? I'm going to just expand it and x. So we had 1, 2, 3. 3 multiplications here. How many multiplications do we have here? We have 1 multiplication here, and then we have 1 multiplication here. So it's just 2 multiplications. But this is because it's small. Like if I did x raised to the power of 4, we're going to have like 4 extra multiplications. But instead of we're just going to have 1 more multiplication. So you can see that in that case to be 7, 3. So the multiplications are growing a lot slower here than here. And when we're going to finite field multiplication is expensive relative to addition. So anytime you can replace multiplication with addition with finite fields, you should want that. So the question now is like, how do we now implement this structure with this Rust pipelining? It was very easy here because this is how I've been programming for a very long time. So it was really easy in this for loop method, but then this one you now have to do. So what you'll notice is that the last thing is multiplied by x, right? And then it is added to the next, second to the last thing. So it means that we're working from the last to the. So that's why we had to do this rev. So what rev would do is that it would reverse the slice, right? So then to give us C3 first, then to give us C2, then to give us C1. Then this one was just because of Ross was complaining about the reference, yeah. So I had to clone it, which is just a copy. It's not really a clone, it's just a copy. Then there's this reduce. So what reduce does is that it takes the first thing in the iterator. So in this case now it will be C3. It's going to take C3 and to store it as the first value, and to take C2 and to store it here. Okay? So then I just wrote this in here. So C3 times x, which is what we have here, then plus C2. Yes. So this answer will now become this, which will become the new accumulator. Alright? Then we'll now do that also times x plus the next one. And then we just continue that way. But this saves like a lot of multiplication. So it's a lot more efficient relatively. It just took a while to figure out. But does it make sense? Not supposed to make full sense. We'll share the code. I'll leave the comment. So there are 3 ways that we have done this now. And I've never entered Lagrange. Bruh.
So for this one, what is like the time complexity? Because I think those functions are like more like infinite.
I think evaluation time complexity is always O of n, right? It's still O of n. Regardless, yeah. Even for this, it's O of n. But big O doesn't take account the constant. Yeah. So once that's like something that can be 2n, and that thing can be 1 million n. From big O's perspective, it's still O of n. But one is definitely faster than the other. So there's still levels in same O of n. So that's just what happened here. the previous algorithms that we did were all O of n, but then this one is now like
Of lesser
faster.
magnitude.
Yeah, like a constant is faster. I was just thinking that whether that's like fully accurate. Because I was looking at the x raised to the power of n, the highest power of x. It's possible that that might contribute, but I don't know. It might be O of n squared, but I'm not sure.
I think we have lesser steps here.
Yeah, this one has lesser steps for sure. You are using less operations because you are not doing redundant steps. We need to do like a proper analysis of the time complexity. So we're good now, right? We evaluate. What's next? So there are different ways you could do interpolate. You could take in the values of x and also the values of y, right? And then you now do your interpolation. But I prefer to assume that x is always going to be, it's not necessary though, but I prefer to assume that x is always going to be 0, 1, 2, ascending. But we'll do both. So the x's are going to be a vector of f64, and the y's are also going to be a vector of f64. And then we're supposed to return what? A univariate polynomial, right? Make sense? Yeah,
I thought we are feeding in the point as an array of tuples.
you could do that. That's fine too. But it doesn't matter as long as both of them are. This one is probably more expensive, right? Because of I'll have to do a check now that the x length is the same as the y length. But if I was doing as an array of tuple, I won't need to do that because it's already guaranteed. So maybe I should just do that. We should do it too. Wants to kill me. Alright now. So now, for interpolate, I think we might need to create some extra functions, like that will make things easier, like way easier. You could do it directly, but there's probably a nicer way to do it. So let's just describe the logic first, and then we'll see what functions we need to create. So the first thing we need to do is, like, remember when we were doing yesterday, so just like the output times the Lagrange basis function plus the output times the Lagrange basis function. So we can do like a dot product between the y's and the Lagrange basis, right? So that means that we need a function that can give us Lagrange basis. It will be way easier, which should be a polynomial. Then we're going to be doing a scalar more of the, okay, so this means that we need a Lagrange basis function. I'm just going to assume we have it now, right? So we're going to multiply each y value with the Lagrange function. So we could do y's dot eta one by one, right? Dot map. So this is the current y. Then y times. So I'm going to implement multiplication for polynomial because Lagrange basis to give us polynomials. Another thing we could do like basis. So now the basis depends on the x, right? So you know the basis is always looking for a particular x value. So we need to know what x value this basis is supposed to be looking for. So this means that just iterating over the y's is not enough. So this way I'm not going to go and use the tuple. Because I could use zip, but then it's just going to be ugly. So I'm going to change it to use the tuple. So that I can have the x alongside the y's when I'm doing my iteration. Right? So now I'm going to iterate over the points this time. So the basis now knows the x that it's supposed to be looking for. Sorry. Yeah, so x and y. So I'm going to pass x to the basis. Now it's going to give me a polynomial that looks for x specifically. Then I'm going to multiply that with the y. So I'm going to just call scalar more, right? Or I can do multiplication. I don't know. Let's see. We'll see. We might refactor it. So these functions don't exist yet. I'm just like writing them out so that times what times y, right? So now we have the each term. So what we need to do is just sum. So I can do dot sum. So this is like the all of Lagrange once you have the basis. Oh, one line. So this is it now, right? This should express what we were trying to do yesterday. It's very naive though. It's like really slow, really slow. But for now, it's fine. Yeah.
So, two questions, sir. The self, is it the same, that self we are returning, is it the same thing as returning that univariate?
Whenever I
The
see,
second one.
whenever I see capital self, it means that we're returning this a new instance of this. Yes. When you see small self, it means that there already existed one, and we're calling a method on that state. Do you get? You want to ask another question?
Yes, then the second one, that basis,
Yeah.
like what exactly does it do?
It's the Lagrange basis. You know that function, that L function that was able to find, let's say, 2, or yeah. So that's what.
Oh, it's inbuilt.
No. I'm going to implement it now. But now another thing I just realized is that you need to know the interpolating sets also, right? Before you can do the basis. And I didn't pass that in. I just passed the x. So this means that I need to also pass the see why I like x's now. I don't want to pass the points. That's too much information. It doesn't need all of that. It doesn't need all of that. Bruh. I'm going back to x's. I don't want x's. I don't want to do that. I'll zip it. So I can make the points now, right? So there's something called zip, where you have 2 iterators, and you want to group them element by element. So 0 from the first iterator, the first element from the first iterator, and the first element from the second iterator, you want them to come out as just one element, on and on like that. Does that make sense? So what I want to do now is I can say like points is equal to x's dot eta dot zip y's dot eta. Let me show you guys in the playground what that looks like so that it's a bit clear. So let's say we have A now, right? And then we have B. Let's say B is 5, 6, 7, 8, right? What is B now? Even though they're not the same length, it would be shorter. I'll do one that is not the same length so that we can see. So it will be A dot eta dot zip B dot eta. So this is now a new iterator that has combined 2 iterators in one. You get? So now I can store this somewhere. Let's say mute new eta. Then we can now say new eta dot next, right? So let me just print that out. So you can see 1 and 5 now. It has grouped 2 of them together. And if I do the next again, it's going to bring 1, 5, 2, 6. You see that? So now what you were asking, what if they're not the same length? So let's say this one was shorter, right? It will do that, so it's still going to do as much as it can, but it's going to get to a point where one of them will say, I don't have anything else, right? And once that happens, it just stops. So the next one will be none, right? So that means that I don't have to do that check whether both of them are the same anymore. It doesn't matter since I'm zipping. It still matters, kind of. It still matters. Well.
Can you write that zip out? Zip brackets A dot theta comma B dot theta.
Like swap them. Okay.
Like is that an alternative way to write it? Like zip.
Yeah.
A dot theta comma B dot theta. Maybe import the.
I think
Yes.
what you're trying to do is like zip, right?
Yeah,
Then you now do A dot eta and B dot eta.
Yeah.
I think you can, but you need to now call it on the absolute part, yeah, from the STD.
Yes.
Yes. Because STD takes self as an argument. So if you call the function directly from the class, then you can pass in what self is by yourself. But if you call it from an instance, then Rust will automatically pass that as self. I don't know if that makes sense.
You pass the instance as a set.
Let me find zip. Yeah, so see zip, it takes in self and it takes in other. So if you call zip from an instance, then self is already known. But if you call zip from std, I guess std iterator, std iterator, I believe, then it would work that way. Let me try that. I don't know if this works, but we'll see. We'll just see if it compiles. Sorry. So it compiles. You see? So this means that this is a zip now. And we can save it the same way we did. Let's make new iter equals this, right? Then we can now do what we just did. Make sense? But why would you want to do this? You could do it for max, yeah? Okay. So now I want to create a zip for the x's and y's with the goal of having the x later so that I can pass it to the basis. That's like that's what I'm doing all of this. So that points equals, or let's say points iter equals x's dot iter dot zip y's dot iter. So now I'll be able to get both the x and y's. So I can replace this entire side with just like the point iter. Then instead of just passing x here, I'll pass in. How did I even know the x? Okay, because of this thing. Okay, I'll pass in this thing too. X's, right? So that I can have the interpolating set. But there's another problem now, right? Huh? No, the denominator we'll get it from the basis. We'll do that in the basis. But now I'm looking at the fact that that x value is not supposed to be. Interpolated set is unique now, right? There's no repetition. Okay, then there's no problem. As long as there's no repetition, there's no problem. Okay. So I think I can get rid of this now, the iter map, and just write x's. Okay. So we zip x and y, right? Then we take each y and multiply with the basis. So that basis is looking for that particular x. And we sum up all the results. This is the literal transcription of like Lagrange that we did yesterday. We just need to fill in the missing pieces. But does this make sense? Is that?
You just said something about the basis.
Yeah.
You said it's doing what to do.
It's selecting for a particular x value.
Particular x value.
Yeah.
So you be the one that will put the x value there.
Yeah. So, yes, you construct it with a particular x value in mind. So if it sees that value, it will output 1. And if it doesn't see the value, but it sees another value in interpolating set, it will output 0.
Output 0. So that one is 0.
Yes.
Now, this sum now.
Yeah.
Good.
Because it's a polynomial, right?
Okay, thanks.
Huh?
Thanks.
Well, I've not implemented sum, sir. We still need to implement sum for polynomials. But I'm missing a lot of features. Yeah.
Moving parts.
Even?
You're missing a lot of moving parts.
Yes. So the first thing we need to do is implement scalar mul, right? So scalar mul is when you're multiplying a number by a scalar, yeah. The polynomial by a number by a scalar, yeah. So in the dense representation, what would that look like? So we don't multiply every coefficient by that scalar. That's how we implement scalar mul. So function scalar. How do you do it in sparse? Is it the same thing now?
Just multiply just coefficient below.
Yeah, the coefficient tuple. Okay. So scalar mod is taking what? A polynomial. So self, we already have the instance of the polynomial. And then it's taking the scalar. It's going to be S64. And then it's going to return what? A new polynomial. Right? So then what we could do now is like say the univariate poly, we create a new univariate poly with new coefficients. The coefficients are going to be from the old coefficients, right? Then so this one needs to own it, but we cannot own it because someone else needs it, right? The old guy needs what it was, so we cannot just take it like that. We can now, right? No, I'm coming. Like, we don't need the basis again. I was thinking that we could intuit it, but there's no need. Don't worry. So we'll map, right? We map the current value of the coefficient, and then we just multiply it by the scalar, right? Then I think we can do cloned, then we can do collect. So what collect does is like converts like something that's giving it out one by one to an array. So it just collects everything for you and puts it in an array. And we need to do that because coefficient is supposed to be an array, right? From collect, okay. So collect takes an iterator and puts all the values in an array. No, normally an iterator gives you one by one. This one you're saying that I want everything now. So you use collect. Collect is basically take it for you and put everything in an array. Does that make sense? I don't know if this builds. I feel like it tunes. But I didn't do the iter. Mad. I feel like we would need it, but let's see. So it seems like we don't. Wait, let me try. Basis is supposed to take what? So let's take the x value. I don't know if that was this. We don't need the real value. And then it's supposed to take the interpolating set, which is a vec of yeah. And then we're supposed to do what? Return a univariate polynomial, right? So, but I'll just not implement it now so that the compiler will stop complaining. For basis, we don't know the, yeah, it's not on any method, right? So we have to call, it's on the class. So scalar mod, did I take a reference? I think I could take a reference, there's no problem with that. Yeah. We're good? Some is problematic now because it needs I think it needs you to implement a trait on polynomials. I think add or implement sum. Why are we implementing sum? Why not just add? So I'm coming, let me implement sum. So whenever I call that dot sum, it will now come and call this guy to know how to sum it. But for now, I'm just leaving it empty. I just don't want it to come. I want to see whether it compiles. So we didn't need clone. So we have scalar mod now.
So, go with the
Normally to have I've copied it here. So because if you look at this now, we're getting everything from self.coefficient. Self.coefficient is not owned by us. It's owned by the univariate polynomial that we're calling scalar mod on. And we don't want to just take that, right? So
cloning it.
So what I was thinking, we'll have to clone it, but we don't have to apparently. I think that's because of F64 implements copy, so there's just no need to.
For that scale multiplication now,
Yeah,
you need self,
yeah.
self and poly. Why did you choose to do that?
Solve then the what?
Yeah?
I did solve then.
Self and then put the univariate poly together. Because when I did mine, I did not do all this stuff. Like I just passed in the vector. So you can take in the vector and return the vector as well.
You mean like your scalar more
Yes.
takes in a vector?
Yes.
It's
Then I
just
didn't want to put that univariate, so just do it directly.
it's just stylistic.
Yeah.
Yeah. I mean, I just want to send a univariate poly again, right? So that because all the methods that I have implemented on univariate poly would follow this, and in the future I might have more things. You get so every time I do a scalar more, technically I'm getting back another poly, right? So I'm just doing that so that I can have the same methods, but it doesn't matter. And passing the array might even be faster sometimes. Who knows? So we're good here. Scalar mod is good. So let's go back to our interpolate. We have everything other than two things, right? We need sum and we need basis. Let's try and do basis. The hard parts. I think I need multiplication and all those things. Are you serious? Oh my god. Sorry. So how does basis work? Well, we need x minus something on the top.
Yeah.
X minus
X, you take like I and j, x minus x j for I multiplied j.
yes. We need to exclude the current one that we're looking for. Right? Yes. Which is like x. No, that's what I was thinking that I need to pass the index. But now I realize that interpolating set is unique. If interpolating set is unique, then I can just use this x and say that okay, as long as the x I'm looking at right now is not this x, then I'm fine. I don't know if that makes sense. So I can know what to exclude by just looking at testing against x. I don't know if that makes sense. We'll see it when I write it. You're saying?
I'll say, like, what if the equation was such that x is having that same value, and you like, let's say you are doing an equation that has maybe x minus 2, and the x you are putting in has 2 value. It will nullify the whole.
What do you mean by two values?
No, like.
Okay, x minus 2, and then you call x plus 2.
X minus 2 as one of the numerators, and then the x value now is 2.
Yeah.
Now it will affect that whole fraction itself.
Yeah. Yeah. So if this basis is looking for 2, it will never put x minus 2 on top. But if it's not looking for 2, then it will put x minus 2 on top, which is fine, right? Yeah. So now, what do? We need to get the numerator, then we need to get the denominator. For the numerator, how do we do this? We need to create a new univariate polynomial for each x minus x minus x minus. And that's a dense univariate polynomial that only has 2 entries, the constant and the coefficient of x, which is always going to be 1. So that's fine. But then we need to now multiply those guys. How did you guys do? Okay, the denominator is a number, right? It's not.
The denominator is fine.
It's a number.
Yeah, it's just a number.
So it's not like a new polynomial. I was thinking you guys did polynomial division or something. Okay, so it's just the numerator. All right, let's start. But first, I think we need to do multiplication. Bruh. So you could do you could have a method in your this thing that has multiplication, but you could also have like you could also implement mul for univariate poly. So this way you can now do like, let's say you had your poly, let's say you had a poly 1, right, as a univariate poly. Somehow. And then you had poly 2 as a unipoly 2. Then you could just do poly 1 times poly 2, right? Rather than having to call like poly 1 dot more poly 2 or something. So that's why the trait implementation is interesting.
That's why
That's
you're
why
separating
it's
implementation.
Hmm?
That's why you separate the implementation.
That's why I'm implementing the traits.
So what me I'm asking is, for that implementation, I just saw that you did it outside the multiplication and the division. I did mine inside.
Your
Inside
poly.
yeah.
Yeah, that's what I'm saying now. Like, Rust now, you can do things like times, right? Like whenever Rust sees that multiplication sign, it looks at the type that you're trying to multiply. Then it goes to check, does that type implement this mul trait? So this mul trait is a trait from STD, right? Mul. So if you implement this trait for your type, then you're allowed to now just take your poly and to use the regular Rust multiplication symbol. Like right now, you're calling yours as a method, right? Poly1 dot mul. Yeah, but you could actually have something that just does regular multiplication or regular addition. So like operator overloading, yeah, for polynomials.
So you don't need to actually write anything.
No, you will not. You implement it. Wait, see. So you see this mul trait. I'm coming. You see this mul trait. So if you now do something like poly 1 times poly 2, this is a polynomial, this is a univariate polynomial. You can use this multiplication sign directly.
Okay.
So when Ross sees this, it now checks the type. It says, okay, the type is poly. Then it says, is there any implementation of the mul trait for poly? If there is, then it takes this one and puts it here. It takes this one and puts it here. And then this just does whatever it wants to do with it.
So you have to keep the rules for the multiplication.
Do you get? Thanks. Okay. I don't know why this is complaining though. Or the output type. Okay.
So if you multiply two univariate poly, it's just going to multiply the.
I don't even know how this works yet. It's dense, right?
Yeah.
I don't know yet. We'll figure it out. I forgot it.
No, because I'm just saying how you are like trying to put two arrays and trying to multiply two arrays
Yeah.
at once.
We'll figure it out now. I'm coming. So the output is going to be a univariate
So
poly.
that mul, is it a trait or a struct?
It's a trait.
Okay.
So we implement the
You
trait.
have declared it somewhere, right?
It's at the top.
Okay.
It's Ross that declared it.
Oh,
So STD ops more. There's more. There's add, there's div, there's mul assign. So mul assign is the one that can allow you to do something like this. Times equals. Why this one is more? Then plus is add. Then plus equals is add assign. So you can implement as many as you want, which will make like people using your polynomial happy because they can just like do times. They don't need to remember everything. Just do regular arithmetic, like as if they're using numbers.
Random question. Does plus.
There's no plus plus in Rust. No. You have to do plus equals 1. I don't know why they don't have that. I don't know what the design is.
It's not great to compile all this.
We compile.
We are not implementing.
Introduce bugs, okay.
So, does it mean that, okay, does it mean that the asterisk will not work for normal integers?
What asterisk, like multiplication?
Yes.
It's work for normal integers.
But if it's small, does it override the symbol one?
Okay, I'm wondering how this works, right? Like once we implement it here, you're saying it might not now work for normal integers again. Okay, no. So when Ross sees that multiplication sign, it's going to look at the type of the thing you're trying to multiply. Yes. Then it's now going to look for the mul on that type. So how do we do multiplication for dense? I don't know how to do this. So when you're multiplying polynomials, the power grows, right? The degree increases. And the degree is directly correlated with the size of the array. So this means that our coefficient array is going to grow. Right? Okay.
I use this zip for this one. Get the same, since they're not to be equal.
Mm-hmm. But if
Then
it might not be the same exactly. It might also not be the same degree. So the first thing we can do is we can get the degree of the result. What will be the degree of the result? So if we had x and x, right? That's degree 1, degree 1. If we multiply two of them, it will be x squared. That's degree 2. What if we had x squared and x squared? That would be degree 4. What if we had x squared and x cubed? That would be degree 5. So we're adding the degree. Is it minus 1?
Adding the degrees and multiplying the coefficients.
But we already have a degree function.
We have a degree function.
Yeah.
We want to have like degree.
Degree.
Degree plus 1.
maybe when we get the result,
Degree-
and divide the degree from the result and from the resulting.
Wait.
Okay, let me get my effort. Yeah, we could do that. So, but
Degree is length minus 1.
degree is n minus 1, yeah. But I've already abstracted that away by having a degree function. So I don't care about the length anymore when I ask about degree. You get? That's the point of abstractions.
But then, why didn't you just like treat the two arrays and
Why don't I just
like see the two arrays and probably like with the index, multiply the two coefficients down with the index, add the index together.
Yeah, so I don't know how it's done. So let's try it now. So I will now take all the ideas that everybody's suggesting.
Degree. 2 degrees.
Okay.
Add the 2 degrees then plus 1.
Why plus 1 again?
I think we want to do multiplication, right?
Yeah.
So let's say polynomial multiplication. So let's say we have two polynomials now.
Mm-hmm.
Let's say one is like 4.
Degree.
4, no, not degree now.
Length.
The number, yeah, the length.
So 3,
So let's say we have one is 4, y one is 3.
Mm.
So the resulting polynomial
Mm.
should be 4 plus 3 minus 1. That should be 6. So that would be the number of coefficients in the resulting polynomial. So that's like in the mathematical side.
Yeah, but
So
that's
no matter,
length. Isn't it?
I'm using,
Yeah, it's in length.
yeah, I'm using length. So I don't know how you're going to do with degree.
It will be easy, don't worry.
But
So I'm just trying to like that.
That's what I say, right?
but if we have
No matter
four arguments, three, that's four.
I'll come out to that now.
And 3 points.
Yeah.
The degree is supposed to sum up to 5.
No, like if you have 4, 3, 4 plus 3, 4 plus 3, that is 7 minus 1, 6. And then it takes 6 points to make a 5-degree polynomial. So I think that's the way.
Yeah. Well, I'm just looking for the simplest.
I think using length is easier.
No.
What are you trying to get? What are you trying to get with that?
So what I'm trying to do now is. So what I'm trying to get the degree is I'm trying to get the length of the new.
The length of the
Length of the new
Is it the length or degree?
of the resulting array.
That's
why I said length of the new array will be
No.
the addition.
Yeah, I'll just do 1 plus the degree.
Yeah, 1 plus the degree too.
You think it's easier to what?
Don't get the degree now.
To not get a degree now. Okay, so how should I do the multiplication?
Get the first term in the first pick one polynomial. Get the first term.
Mm-hmm.
Pick the coefficients. Add them. Multiply the coefficients by the coefficient of the second polynomial.
All the coefficients of the second polynomial.
Yes.
Mm-hmm.
Yes. Then add the exponents of that. That first term. Add the exponents together.
Yeah,
You
it's
get.
fast.
Yeah.
No, continue. Continue. And yeah, but she's doing this fast.
Yeah.
So you're adding the index, right? You're adding the exponent, sorry.
Does it not work for?
It should work for sparse.
But then
Yeah, but
I'm sure it will be similar idea.
no, for this, I think for dense, I think you need to add
It's the same idea.
the index here.
It's the same idea.
Yeah.
Like the only difference is that our exponent is in the index and our exponent is in the tuple.
Yeah.
So it's the same
Same
idea.
idea.
Yeah. So you were saying that you pick the first element from, then you multiply all the other ones, right?
Yes.
You are pushing into a result, right?
Yes, into a new polynomial.
Yes.
They will not perform addition of everything. let's say 4x the first time for the first polynomial, then do another multiplication for the second one, just like normal
Distribution.
yes, then do the second one, add it to the new polynomial, the
So
third
you
one.
implemented add for you to implement more.
Yeah, I think you should.
I think I have to.
I think so.
For collecting like terms.
I think for collecting, I think
Not really for
collecting like
I
terms
think
you have to do.
collecting lifetime can have its own like.
Let's implement add
Just
first.
collect lifetime.
But I
Yep.
think the way I did it,
Add is easier.
in the loop, it just
Yeah, there will be a way to like resolve everything.
yeah.
I'm just trying to make sure you get that. Right, so we implement add now. So how do you add dense?
So it's just by getting them.
Is there a default like
So if we're adding dense, what happens? We're just adding now, right?
The way I did it is I picked the two values, right? Maybe I picked the first one. So I multiply both of them and I also add their index. Then I put it inside the array because I already know the
Full length.
of the array. So
Yeah.
I just return it inside the array. Then the next one, I will
Yeah.
loop again and check the
Yeah.
indexes.
Yeah.
If it is equal to them, I'll just add it to what it
Yeah.
is.
Yeah. Yeah. That's how you collected like terms. Yeah. But if you wanted to add two polynomials, how would that work?
I think the polynomials are the same exponent and an exponent.
So it's just like element-wise addition. So we're just zipping, right?
The zip, what is the length addition?
So you need a larger one.
yeah,
But
you
for
just
them,
find like the
length
large.
cannot be.
You find the
No,
large
it can be
ones.
different.
Yeah.
But why didn't any polynomial?
You can slice the length of the smaller one first.
Yeah, you could do that too.
You can take the new
And
one
add it.
and use the
What would be the easiest way to do this?
but the new
But
length.
for them, don't we like add zeros to make up for the ones that are not present?
You just check the
Yes, but you might have, because now we're adding two univariate polynomials that were created in two different places. So someone might have created something raised to the power of 5, some might have created something raised to the power of 7. They didn't know that each other will exist. But then when you're adding, it just adds like that. Yeah.
This is why it's not dense. That'll be like zeros. You can use the length of the local
Yes.
polynomial to determine the length of the polynomial.
Yes. And another thing is that we could just duplicate the bigger one in the results. So like let mute results, right, is equal to if self dot degree or len. It doesn't matter, both of them can work, but I'm just like which one will be better? I'm using degree. If self dot degree is less than RHS dot degree, then that means that what? Self is smaller, right? So that means I would just clone the RHS. Then else, I just call it bigger and smaller. And I hate this though. How are we consuming self? How are we consuming them? So else is the other way around, right? That's like oh. Oh, I don't need to do this again because it's already it's possible, right? So now we know the bigger one. Then all we just need to do is modify the bigger one only at the places that the smaller one reaches. I don't know if that makes sense. So it's like can we zip? Why not?
I think we can then add the rest.
We should go to zip. I'm fine. Let me do bigger, right? The eta. No, bigger the coefficient, right? The eta. But you don't want to modify the bigger one. So the eta mute. Then dot zip smaller dot coefficient. The eta, no mute this time. Because we just want to, yes. Then dot map, right? So we'll have the bigger coefficient first. So I'll call it B coef. And then we'll have the smaller coefficient. So small coef. And then I'm going to just say B coef plus equals the small coef. And then that's going to be my
Sorry.
Why is it supposed to be mutable now? Yeah, I'm coming. Yeah.
At what point does it know, like, I was thinking maybe there could be like something like an if statement to check if they are of the same, like,
I think it is.
oh, okay.
Like I'm using the length to check which one is bigger.
So, yeah, you're checking which is bigger and returning it. So, when you want to add, I think you're supposed to like, or maybe all these zip map has done everything.
I don't yet know. This is not compiling. I'll explain it once. Why is it not compiling though? Feels like this should compile now, right? I need to do star. Let me see what the compiler is saying. Oh, it's complaining about this thing. Oh, that's fine now. I don't mind that. I'm sorry.
So, sir, the smaller cell that it is taking in as input, what is it referencing?
I'm coming. Sorry. Give me a sec. I just want to make this thing work first. So add traits requires you to does add force you to I don't want to consume now. That doesn't make any sense. Like I don't want to consume it. I don't want to consume it. Why must I consume it? Let me call the out. Oh, I see. It forces, but I can say that this should be a reference, not consumed. Yeah. So what's going on here? Bigger is already mutable now, is it not? RHS was what? Have I implemented clone for this thing? I'm coming. I will explain once I'm done. Is it still complaining? But it has stopped complaining now. No, but it's complaining about this. Why? He's expecting F64, right? What is he getting? Oh, I don't need to collect. I just need to. But I need to collect. But I don't need to collect.
It's a map already.
Yeah, the map already. Yeah, no, the problem is that I'm doing a an assignment. An assignment does not return anything. So I'm collecting nothing. Like my map is not outputting anything. I don't know if you get what I mean. So normally you're supposed to take an input, do something to the input, and return that thing out. But I'm not doing that here. I'm just like modifying bigger directly. And then I'm not trying to collect nothing, which is why it is like angry. But the question now is like, what do I do then? If I don't collect, it's going to be lazy. Like, Rust is lazy. So it's not going to actually do anything. How do I force you to do something? Well, four will be easy. So what?
The bigger, the coefficient would have changed, right?
Yes. So I want to just return bigger, right?
Why can't you just return it like call the bigger then return it from the bigger?
Return what from bigger?
Return the coefficient.
Like I'm modifying bigger right now, yeah?
Yes.
So technically I'm supposed to just return bigger.
Yes.
That's my goal. But Rust is lazy.
But it have already modified it now.
Yes,
But
but
when you call bigger, we do not
updated. Rust is lazy. Let me show you what I mean by Rust is lazy. So let's say I have this A, right? And let's say I want to modify each element in A. So I say A dot iter mute, right? Dot map value, and I say value times 2, right? This is not going to do anything. Like when I run this code now, how do I show that it doesn't do anything? Okay, let me make this mute. Okay. This should work, right? So that should technically multiply every element there by 2 and assign it back into A, right? I'm mutating it. Now if I print this out, it didn't do anything. The only reason why it should do something is when I now do doc. I can't do the collect now. But I can do collect now. But I want to not use F64 or anything. I have to use the. It's collecting nothing, right? Can this work? Okay, so it works. So now that I've collected it, it would now trigger. So Ross is like, you created this pipeline and you never used it. So I won't waste energy doing it. You get? It's like I'm not going to waste energy doing it. And that's why it's lazy. So that is actually the same thing that is happening here. In the sense that I'm saying modify this for me. But because I'm not collecting, it's like I'm not going to waste energy doing it. So now I have to force it to do it by collecting. So now it's going to do it. But it's asking me to. So if you know you're not going to use what you have collected, just put underscore. So now I can just return bigger. And it's building. What have we done though?
From the beginning, please.
Sorry.
Yeah.
Once you're using zip now,
Yeah.
you have like the bigger array,
Yeah.
the smaller array.
Yeah.
Let's say you have like 1, 2, 3, and you have 1, 2.
Yeah.
And depending on the order, the way it's going to be, like what is going to happen to like the last element when you're using zip.
Which last element?
Like we have 1, 2, 3, and we have 1, 2. Once you're using zip,
Yeah.
you know that it's going to like go
1, 2, and stop there. Yeah.
Yes.
That's fine, right? So why it's fine is because of, let's say I was adding 2 polynomials with 2 different degrees. right? You can see the iPad. Okay, let me show you the iPad. So let's say I was adding 2x squared plus 5. Yeah.
Imitating a bigger
Yes.
array, so that variable still remains.
Yeah. Huh? Am I on the meet? Am I still sharing on the meet? Let me check. Yeah. Yeah, I am. Okay, so 2x squared plus 5, right? And I want to add just 2x, for example, or 2x plus 6. If we look at the dense representation of both of them, this is what we'll see, right? The constant will be there. There's no x value. There's a 2x value. Why this one, the constant is there, and then there's an x value. But this all, right? This is where it stops. They have different lengths, theoretically. Now, when we're adding, this 2, there's no 2 square in the other side, or no x square, or no nothing, right? So technically, anything away from the boundary is not touched. Exactly. So that's why it is safe to just add based on the small index or based on the zip. You know, the zip will stop at that point. So we just add like this. That's 11, 2, and then we just copy the rest back. So the way I'm achieving this is I'm mutating bigger to change this and change this. But then I leave the rest. So I just send that back. Does that make sense? So this is how we're doing the addition. Take the bigger one, copy it as a result, then only modify the places that the smaller affects. Does that make sense? Then it's just not using Rust to.
So what if you have something like degree 4 and degree 2? So there's like 2 extra.
Yes, so the 2 extras are not touched, they'll be returned.
2 of them are can be bigger.
2 of them?
Are the bigger. Or just
Yes, 2 of them.
bigger. What do you mean by the bigger? I thought that bigger is like the highest one.
The bigger is the polynomial with the highest degree.
Okay.
Or highest length.
Okay.
Yes. And addition only affects where they overlap. Yeah.
Sorry, I have to put something now. What if we had degree 0 and 2 in 1? 0 and 2 in 1, right? Sorry, exponents. Exponent 0 and 2.
Coefficient or exponent?
Exponents.
Okay. Okay.
That's the
Constant and x squared.
X squared.
Yeah.
Yes. Then you now have x1, x raised power 1, then x raised power 7. So that means that, you know, you said that. I'm trying to think about maybe when I write it down to make sense.
Okay, let me write for you. So you said x squared and what? Constant, right?
Yes.
So this works for it, right?
Yes.
Then you now have, let's say, 3x plus x raised to the power of 7.
No, x raised power 3.
Oh, okay.
Plus x raised power 7. So can you add x raised power 2? Wow, there's something I'm trying to make. I'm trying to make it.
X raised to the power 2 to which one?
You know, when there's like a gap in between the largest one and the larger umbrella,
Mm-hmm.
does it cut? Like, does it cut it?
So, you know, in dense representation, there's no gap.
Yes, it's represented by 0.
Exactly.
Okay, so there'll be an addition operation on 0 as well.
Yes.
Okay.
You get. So this x3 will be added to the 0 of the x3 in the other one. So it just like collapses. Does it make sense?
Yes.
So does everybody understand the addition?
Not in the code.
Okay, not in the code. But you understand the theory. I'm sure there's a way better way to do this. This is just like on the fly. So the first step was to get the bigger. and the smaller, right? So that we can do what we want to do. So what I did was I said if self.degree is less than RHS.degree, right? So we have two polynomials, right? One is called self, one is called RHS. So if self is less than RHS, that means self is the smaller one, right? And RHS is the bigger one. So that means that I'm supposed to return RHS as bigger, right? I don't know if you know how this structure works. Like you can return from an if. So RHS is taking the place of bigger, while self is taking the place of smaller. And then I made bigger mutable because I want to be able to modify it. And so that's why I had to clone. But self doesn't need to be mutable. Self is just a reference. Then likewise, if self is not less, then that means self is either equal in length or it is greater, right? In that case, I can pick, if they're equal, I can pick anyone as bigger. That's fine. So it still works. But if self is bigger, then I also pick self as bigger. So that's why I just said else. So self will now be the bigger one, and RHS will be the smaller one. So now I have identified my bigger and my smaller. Now I only need to modify bigger based on where smaller overlaps. So that's what this is doing. So the way we're doing this is that we're now going through bigger's coefficients, and we're creating an iterator from it so that we can get it one by one. But we're creating a mutable iterator. What this means is that the value it is giving me, I'm allowed to change it. I need to change it at the source for me. Okay? And bigger is the one I want to change at the source. So I'm getting each one by one, and then I'm changing it at the source. So I zip it with the small one. This way, the way zip works is that it stops once one of them is done. So it's going to stop one smaller as exhausted. But then it's still giving me constant, x1, x1, x2, x2, x3, x3. So if smaller stops at x3, it won't give me x4. It will just give me none. I need to stop. And that's good because I didn't want to modify those ones. So then this is now the thing that takes what it has given me from both and does something with it. So what is it doing? It's basically just it's adding the small to the big, and it's storing it back in the big.
So zip does the actual work.
Zip does the work of slicing.
Yeah. So
Yes.
the question I was asking about the checking, like
The
if
length.
the index, yeah, like
Or has
the
reached the
same,
end.
the
Yes,
index
it's
are the
zip
same
that is
before
doing
you-
that.
okay,
Yes.
zip does it, okay.
Then that star is how you. So when you borrow something that you can change, you're not giving the thing. You're giving an address to the thing, which is a reference. So you now say, if you just do b coefficient plus this, you're now saying address plus. But then what you actually want to change is the thing it is pointing to. So that's why you put the star. The star is now saying whatever is at this address plus add the small coefficient to that thing. You get? And modify that. Does it make sense? Are you sure?
Yeah.
Yeah.
Yeah, so the question I was trying to ask before
Yeah.
was at the input level of this function,
Yeah.
the big self now, like the RHS,
Yes.
we understand it is saying that this RHS is a type of something already defined, which is the univariate poly. Now,
Yeah.
but the small self now,
Yeah.
what is it like? What type is it like? Saying specifying for?
It's
Like,
all. It's
not
also
defined yet. Also,
no. It's defined. Both of them are. How do I put it? So when you see small self, it means that there's a poly already, right? That you will now call dots. Dots. So anytime you have a structure and you call dot something, it's always represented as small self, right? So that thing in front will be passed into small self. Let me show you how you might use this. This is not how you actually use this though, but you can do like poly 1, which is a poly, dot add poly 2. So when you have something like this guy goes into self, y desired shifts to
Come
right
to-
hand side. Yes.
Oh, okay.
But you can also do it based on the question that I asked last time. If you find the absolute part to add, you can just do add poly 1, poly 2.
The two of them will have the
Then this
same-
one will be
yeah,
self,
self.
and that one will be big self. But we're not using all this because Ross will do it for us automatically once we
So
do
this,
poly
for the
1
first one,
plus poly 2.
for the one that is now the second one, the poly one before it was before this add function was called, it's referencing the univariate already.
Yeah, it's already an instance of univariate polynomial. Yeah, so you have already created a univariate polynomial and you stored it somewhere. But even this one too is created also. So let's test add.
Wait, are we done with,
Oh,
you know, the part where you have to copy the remaining?
Sorry,
so wait, I'm coming. Sorry. So once we modify bigger, while modifying the coefficients of bigger, then I'm doing this so that Ross is not lazy.
Okay.
So now everything has been modified, and now I can return I'm creating a new univariate polynomial that is using the modified coefficients of bigger. Does that make sense? But actually,
The remaining ones that are not modified.
yes, exactly. So it's taking everything at once.
Yeah.
Hello?
Sorry, my question is, I just want to understand this dereferencing better.
This one?
Yes, like when you dereference the three coefficients,
Yeah.
the S, why you not doing the same to S?
For this?
Yes.
So I get what you mean. So it's like Ross is doing that for me automatically. That's because I'm not modifying it. Like, but when I'm modifying it, I need to be explicit, kind of that I'm pointing to what you are pointing to. But Ross is like, the type of this is a number. This here is an address. Maybe the address is pointing to a number. Let's check. Oh, it is. Or you add. Do you get? But then this one you have to be explicit about it because you are mutating memory. Make sense? Does this make sense? Does the code make sense?
Can you scroll down, please? Okay.
So let's test add. I need two functions. I need another one. So let's just do x. Right? Just so that it's easy. So x is going to be 0 for the constant, 1 for the coefficient of x. This is x. These are represent x, dense. Right? There's no constant. That's why it's 0. And the coefficient of x is 1. So this is, but Ross doesn't know that this is a float when it's obviously a float. Okay, so now we can test addition. Now you see how I'm able to just do poly 1 plus poly 2. But I wanted references, so it would require me to put a reference there. So now I'm able to just add two polynomials like that. Like I don't need to do dot add or anything, just add them. I can see their numbers. And then I can create what am I expecting? What are we expecting the sum to be? That would be 1 plus 3x, right? Why did I do just x? I thought I was doing multiplication, so I was like, I didn't want something too big. Let me not just do x. Let me do x plus, let me do 4x plus 3 plus, let me do eh? That's so annoying though. So the constant is what? The constant is 3. Then x is what? 4. No, let's do it. So this is what 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's another way to do this though, right? You could do concat. Then you could do concat. Let's try that. I've forgotten the syntax for that though. So let's coif, right, equals like vec of 3.0, then 4.0. How many zeros are we going to have? 8? 8, 10, 11, yes. We're going to have 8. So you could do vec of 0.0, then you duplicate it 8 times. Then you can now do vec of 5.0, right? So it's now, how do you combine this? I've forgotten. Can you just do concat? I don't know if you can just do this. Let me see what the error is. I'm coming. Let's see the method. So concat takes what? It takes self, and it takes just self. Okay, no, see it down there. Oh. You put them all in a vec. Yeah, in an array. Nice. Hmm? Yeah, I could use extend too. Yeah, I could use extend. So like this, right? So you put all the things you want, then you now do the concat. So not bad. So yes, this is it now. So we just create. Sometimes I could have done this down here also. Cool.
I think it should be 9 zeros.
9 zeros? Why do you think so?
The length is 12.
Okay, degree 11 needs 12 elements. And this is 2, 8, 10, 11. That's true. 9 zeros. Right? Right? Which point? I think it makes sense now. Yeah, because your degree should always be 1 plus, right? So a constant is degree. Constant is x to the power of 0, which is at index 0. Yeah, exactly. So 11 is 12. Yeah, it's fine. So this is this polynomial. Now when we add it, what are we expecting? Let me just copy it. So here, this is what we're adding, right? So we're expecting results to be what? Constant, that's 4 plus 6x 3x squared. We'll do another one again. I'm probably going to get rid of that thing that I duplicated. Is it? No. Because that's bad because of your your logic might be wrong. You verify it, right? Yeah, true. Okay, let's do this. What's constant? 4, 6, right? There's 3. How many 11s? 5 is too far. It's 8 now, right? Because of we have. So I need vex, right? It doesn't seem to like. Why is it comparing? Nice. Then I'll just make it fail intentionally. Just so that I know that I'm not being deceived. for assert equals, you need to do debug. This is all. You need to do partial equals to before you can compare. It's Rust. What's the problem? Explain univariate line what? Line 149. Oh, I'm supposed to be comparing two univariate polynomials. I'll just take the coefficient of the result and compare that. Finally. So it failed, and hopefully it failed for the reason we expected. So it passes. So we have addition. Bruh. Are you serious? So multiplication will be crazy though. So for multiplication now, how do we do this? So we have an array, right? Let's try and do this one. I also wanted to do this. Do we have to? We might have to. But I don't know if it's necessary. Dense. So dense is 5, 0, 6. Yeah. So how do we do this? The new array will be of length what? Do we need to know that? We need to know that.
N plus n minus 1. So that's like the length of the two arrays added minus 1, which is like the degree plus, I think degree plus 1.
Degree plus. It's like degree plus degree plus 1.
Yeah.
Yeah.
So now with the length of the
Yeah. Okay, but if we don't know it, how will we do it?
Change the length of the
But then I think
length of
like
the longest one and just to the
if you don't know what,
Okay, so okay, now assuming we know it, what do we do?
assuming we know what,
Now we know the length, right? What do we do now?
it's going to be a for loop.
Okay. Over what?
So we might use the bigger one.
Okay.
Then when we are looping, we are now going to have like a. So now we've already initialized like a vector.
All zeros, yeah, of that length.
Yes.
So we can index
So
it.
now it's not going to be like. Now we have two iterators, I and j, because we have been looping through these two.
Okay.
But then the reference, like the first one is going to be the bigger one.
Okay.
So now what we want to assign is going to be that vector, the array, I plus j equal to like the multiplication. It's going to be like plus equal to.
So where are we indexing in the result array?
The result
How do we
array
get the
is
index?
going to be like the addition of I plus j.
Of the two indexes?
Yes, because I think when we multiply, at the end of the day, we're still going to add the like terms.
Yeah.
So, and then if you notice, the like terms have that I plus j similarity. So most of the terms that we add, like we are collecting like terms,
Yeah.
they have the same I plus j. They have the same index in the
Yeah, the like terms will have the same index and then
Yes.
because there's only one spot for x squared.
Exactly.
So if you have multiple things like x squared, so all go there.
Exactly.
So plus equals, right?
Yes.
Okay. So let's now do it on paper. Right? So this will be 0, 1, 2, right?
Yes.
Then it's also 0, 1.
Yeah.
So 0 means like x raised to the power of 0, x raised to the power of 0, right? So if you multiply two things that are x raised to the power of 0, x raised to the power of 0, you're expecting something that's also x raised to the power of 0. So that means the index should be 0 still. And you're saying the index computation is 0 plus 0, right? Which is still 0. So that's correct. So we'll do 5 times 6, which is what? 30. So 30 is going to index 0. Okay, let's continue. Then what's next? You do 0 and 1, right?
Yeah.
So that's like x raised to the power of 0 and something that has x. When you multiply two of them, you're going to get something that has x.
Yeah.
So that's supposed to be 1. And that's 0 plus 1,
Yeah.
which is 1.
Yeah.
So that's good. So that's 10. So now if we do this and it's always the next one, then technically we don't need to know the length of the resulting array. Do you get? We could just push. So the question is, will it always be like that? But we'll see. Let's
I
continue.
think we need to know.
Why?
It's not always like that.
Hmm?
It's not always
It's not always
be like
like that. Prove it.
Oh, let's continue.
Let's continue first. Yeah, let's continue. So the next thing is this.
Sorry, before you continue, I want to understand like what you're using to perform this multiplication so I can see.
What I'm using to?
Like how you're performing this multiplication.
Yeah.
I want to understand like
The,
what you're doing.
so we're looping, right, over one of them. I think the other we loop doesn't matter, whether the bigger one or the smaller one.
Okay.
But now we're starting with this bigger one, right?
Yeah.
So we loop, the first element is 5.
Okay.
Then we use that to multiply all the elements there.
All the elements.
Yes.
Okay.
And then we insert it into this result array.
Okay.
The index we insert it into is the summation of the index of the two things you
Will be the
multiplied.
Will be the same now.
What do you mean the same one?
Like
The same index.
we are multiplying 5.
Which is our index 0,
Yeah, at index 0.
and 6,
6.
which is our index 0.
Come back to index 0.
We're coming back to index 0 because of when you add
Five
the
is
two index,
Yes.
5 is 0 and 6 is 0. When you add it, it's still 0.
Okay, you added 2 indexes.
Yes.
Oh, okay.
Yeah.
So when you move to 5 times
2.
2, you added 2 index
1.
1. Okay. Then
So
the next,
adding the two index like adding the exponent.
yes, the exponent.
Yes, it's exactly equivalent.
Okay.
Then we'll now
So
continue.
We'll now continue.
So we're done with 5 now.
We are moving to 0.
We're moving to 0.
Okay.
So 0 is going to be what? Okay, so it's not the same.
Everything.
It's not the same.
Yeah.
You cannot just push. You need to.
Yeah, so we have figured it out.
You can create different
can't push.
polynomials for each multiplication. Then you add them together.
So for 5, like,
That one.
What did she say? Sorry, kids, what did
So
you
you
say?
can do what?
You can create different polynomials for each multiplication form.
So you use the first one to multiply everything, one polynomial, and this is the
Add
second
them.
polynomial.
What of
And then everything now, add them together.
Well, that's like so.
What
That's
does-
like nested.
No, it's not necessary.
It's not going to be nested though.
It's the same running time.
Like
Wait, let's see.
That's probably
Wait, let's see. Let's finish this. Let's finish this first. Then we'll now do it. So 0 times 6, right? Will be at where? 1. Right?
We are at index 1,
Yeah,
yeah. But the
yeah.
value is
Index
0.
1, yes.
So it's coming here.
Yeah.
I'll just leave it like this first.
Yes.
Everything is 0 now.
Sorry.
Just go to 2.
Then 0 times 2 is also the same thing. But where is that going to be at now? Index 2.
Yeah.
So that's 0 here, right? Following?
Yeah.
Then 2. 2 times 6 will be at index 2,
Yeah.
which is 12, right? Right?
Yeah.
And then 2 times 2 is 4, which will be at index 3. So that's here. There's a pattern. There's a
So
pattern.
we are not pushing, right? We are using this.
Yeah, we're not pushing. I'll find a way to. 30, 10, 12, and 4. What polynomial is this? This 30 plus 10x plus 12x squared. So is that what we're supposed to get?
Yes.
4x cubed, right? Plus 12x squared plus 10x plus 30. Okay. Now let's do the other method. So in that case now, you are going to use 5 to multiply everything, and you get new polynomials. Okay. So the first polynomial is what? But then you're still adding the exponent. You're still going to add the exponent, right?
Yes. Yes, that's the exponent. When you add the exponent, you're going to get.
After you add them all together.
So it's like you're
Wait,
adding vector.
No, you're not.
I don't even get
Alright.
it.
But
What are you,
No,
what are you,
once you
what
multiply
polynomial are
now,
you
you're
trying to
not having
create?
no, like
She's saying
we're
that.
trying to use
Yeah,
our
which
method.
yeah, I didn't really
It
get
will
it.
work, but it's not complete. It doesn't feel complete
Okay,
yet.
create polynomial for each.
Yes, for each.
Then what do
Okay,
we now
because
do?
how do you know
Add,
the new
add
one?
everything.
Yes,
The
because
new
Add.
polynomial.
like this 0 now is not just 0.
Exactly.
It's 0x. And this 2 is not just 2. It's 2x squared. So you need to carry that information along. So that when you multiply 2x squared with 6, you're getting 12x squared. So you don't just put it at index 0. You need to put it at the square position.
Yeah.
So this means that it's still doable, but you need to pad with zeros every time. So the first time, it's using sparse, that's why. So the first time you push into an empty array. I think you also can push now, right? You can just push. Yeah, you can just push. So this is what I'm thinking. You initialize the array. The first one is just like this. So you do your multiplication. That's 5 times 6, which is 30. And then 5 times 2, which is 10, right? But you know the second one is an x. So this means that you should shift a bit. So just push a random 0 starting, alright? And then just do 0, 0. Then the next one is an x square. So you shift twice. So that's 0, 0. And then 12, 4. Then you just do the polynomial addition that we had, which is going to be like 30, 10, 12, 4. Which is still it works, right? Both of them work. Which one are we implementing?
How do we implement the first one?
The first one,
Programmatically.
how do we implement programmatically? It's probably two for loops.
Okay.
Two for loops with enumerate, but it's going to be I'm not going to use regular for loops. I'm not using a map and all this thing.
You're not going to use regular for this.
I'm going to use regular for loops. So we'll try and do both. I'm coming. So for I in what? Doesn't matter. The other doesn't matter now.
Yeah.
Right? No. So the reason why it's graying it out is because of this to do. Okay, so what am I supposed to do? I'm supposed to. Yeah, I need the result. How many is it going to be?
Degree n plus. Okay.
We need to-
Degree plus degree plus 1.
So a degree 1 polynomial times a degree 1 polynomial will be a degree 2 polynomial, right? So we can get the degree of the result, but you know that you need n plus 1, d plus 1 points to represent any polynomial of degree d. So that's why we need to do 1. So it's basically like the new degree is basically going to be like it's going to be the degree of plus the degree of this. But then we need plus 1 points, right? N plus 1 points in order to. Why are you complaining?
U size.
Constant.
That's plus one. They also add. After when we were trying to get length plus length plus something,
Mm-hmm.
I was saying if you're adding degree now with degree
Mm.
plus degree is another one. If it was
Yes.
length, you have
Yes.
length plus length minus 1.
Let me see what the compiler is saying. I think it's because it's not constant or something.
I think it's U size. We're trying to add a U size thing.
So what's the length of the distance supposed to be U size now? It's non-constant value. So how do I do this? Oh, it's a vec. Sorry, I was not using a vec. I was using a slice. Okay, so this works. So now we have an empty result. So now we just do this thing we were doing. So we know that the new index is going to be I plus j.
Yeah.
So we just say like result
What's
I plus j is equal to plus equals because it might reoccur.
Yeah.
Plus equals what?
Self of I.
So that we're returning univariate, right? For loop for the win. So let's test this. It's unwise to multiply these two, right?
Those two examples that we did.
Use all the use of me. Okay. So we just create the polynomials here. So the first one was 302, right? What was this? F of x is equal to what? 3 plus 2x squared. What's the second one?
That was 2x plus 5 and 2x plus 1 plus 6.
It was 2x squared plus 5. And then it was 2x plus 6. What was that? 6 2. Yeah?
Yes.
Well, I was supposed to create a univariate polynomial. This is why I now need univariate polynomial dot or new, rather than having to type it every single time. It doesn't know that it's floats. This is so dumb. This is so dumb. Almost everything we're doing here is not efficient though. Like it's just naive. Okay, yeah? And since we implemented the mul trait, we can just do the multiplication direct. I think I did yeah. So why I'm doing this is because of, if I don't do this, whenever you multiply two things, they will disappear. Like you get the result, but those two things that you multiplied will just disappear. They'll be destroyed. Because you can say that this is not a reference. This is ownership. And then this one is also ownership. But it's not every time you want that. So I'm making a reference, exactly. No, output will still be output. So that way, rather than calling just poly 1 times poly 2, I'll call a reference to poly 1 and poly 2. So I'm going to get a new univariate polynomial. Then this univariate polynomial, rather than just creating a new one, I'll just get the coefficient. So the result of this multiplication was supposed to be what? Oh, this is what we did just now. 30 plus 10x plus 12x squared plus 4x cubed. Choose a vec of what? 30.0, 10.0, 12.0, and 4.0. So, yeah, I like to make it feel first then. So the compiler might just not be seeing my test for whatever reason, and I'll think it's passing. So it's good. This one works. Now, what if we wanted to do the other way?
I just feel like consider me just basic.
It's just basics now. We're almost done. Let me see. So you guys should play with these algorithms and see if you can figure out better ways, because this one, what we have done right now, are not the best ways per se.
Excuse me, I have a question.
There are ways to get better results.
I have a question.
Yeah.
So, when you're writing code, obviously sometimes you don't write the most optimized code.
Mhm.
Like, how much does that matter?
How much of it matters?
How much does it
So I have optimized code.
I know, of course, it matters, right? You know,
So,
first is clear.
like ZK now, right? The entire industry is trying to build fast provers and verifiers. So whenever you whenever you do a computation locally without trying to prove it, it's blazing fast, like blazing fast. CPUs right now are really fast. But if you do the same computation, but then you want to be able to prove it, then it becomes really slow. So let's say like right now maybe like 1,000,000 times slower, for example. Like it is way slower to do something natively and do it and prove it. Like it's so much slower. So the industry right now is trying to make that as fast as possible. So the goal now is to make faster and faster provers. So in our space, optimization matters a lot. You get? That's why I'm always talking about like optimization. Now we're not an expert at optimization, but that's the next phase for us. We want to start learning optimization. That will require you to go into like assembly, for example. Know how your code turns into machine assembly, for example, and then see how you can change stuff here and make the assembly much smaller. And also understanding how the processor works, like the cache lines and all those things, then taking advantage of that. Because I believe that once you fully understand something, you can maneuver your way however you want to get to your desired goal. So that's the next phase for us. Where I have to buy a Windows PC, for example, just because of I want to use Linux. Ubuntu has better tools for doing all this. Not that they have better tools. Mac has good tools, but all the resources out there are usually using like Linux. So it's like I can be trying to figure out. It's there. But I don't want to learn two things at once, right? Because I'll have to learn how is this thing that is being done in Linux, how can I do it in Mac? And then I also need to learn performance engineering again. So I'm learning two things at once, it doesn't make sense. So I'm thinking that, okay, use Linux, learn performance engineering. Then when I'm done with that, let's say come back to Mac and learn how to do what I know how to do on Mac. So 1-1. But it's really important. It's really important.
But the end goal is Mac.
Why not stick to us? Why not stick to Linux? My Google Meet calls where the microphone was not working. So I was using it for a while. I was like, wow, Mac, Linux is so good, But then when I was on the call, my microphone would not work. I had to restart. Mac just works.
We entered back the group chat.
But yeah, some people will not agree. Yeah, isn't Linux, sorry? Is it using Linux? Call someone. Yeah, isn't Linux?
So as a programmer,
ZK.
you have to, when you write a code,
Yeah.
actively research on how to make that like code better.
Yes. Not every time. Maybe initially, maybe I've gotten yes. Oh, you are doing two things now. You need to learn first, right? So you don't need to worry too much right now. Just learn, make it work, yes. Then when you now know how it works and you can now start focusing on making it faster and all. So usually it's like make it work, write test. The test is make sure that it always works. You get. Then you now start modifying with benchmarks. Right? You have something that can measure how fast it is going. Then you start modifying. You can make a modification that might change the logic entirely. Your test is there to help you make sure that it's still correct. And then you just like have this loop. But you don't need all those now. Right now. So the industry, okay, and that thing is that they are not yet so focused on optimization on like the assembly level. It's not like there's still a lot of speed up that you can get from new research, right? Like a new protocol, for example, or a new polynomial commitment scheme, or a new way to do sum check. Like new papers are contributing more to faster speeds than just like pure software optimization, right? So you can be optimizing a way, like a protocol, like be the best optimizer in the world, optimize that for five months, and then a new paper will come out, and this guy that does not even know anything about optimization will implement that new paper in the most naive way, and his implementation will be way better than your own implementation. That's because of the speed up came from the different algorithm. Not necessarily, you're trying to optimize a worse algorithm. You can do as much as you want, but if there's a way better algorithm, it will beat it. Yes, but obviously, if both of you are now implementing that same algorithm, but you have more performance engineering experience, then you'll be able to implement that particular algorithm faster. You get? So there's a balance, right? So right now, most people don't focus. They're not focusing too much on. They are focusing on it though, but they're not focusing too much on it. Does that make sense?
Yep.
Okay. So what's next? What's left? I'm tired. Can we do the basis already?
Yes.
So what is required for basis now? The numerator. So we need to create new polynomials. And we need to multiply them, which I already know how to do. Good. We just multiply. Then what do we do? How do we get the denominator?
So we define an x. That is a polynomial with coefficients of 1 and
Are you evaluating it?
no.
Well, we could evaluate it too, right?
Oh, that is
Huh?
are you trying to evaluate?
We could, technically. Like what I could do, you know all we are doing is that we just have the numerator,
Yeah.
then we evaluate the numerator at the thing we're looking for, normally. You know how we do, like, we write x minus 2, x minus 3, then we now do divided by, we just copy this down, but instead of x, we replace it with what we're looking for. Right, like 1 minus 2, 1 minus 3. Does that make sense?
Yeah.
So I think we could do that. So the first thing I'll do is I'll just get the numerators. Then I would evaluate. Then I'll multiply. Wait, we could can multiply first. Let's just start. All this thinking is too much. So how do we do this? We need to go over the interpolating sets, right? So right? Eta map x prime, right? So this is so if our tabulator set is 0, 1, 2, this will be 0, 1, 2, right? But depending on the x we're looking for, we don't want to include. So are we supposed to use map then? We're not supposed to use map then. We're supposed to use filter map. Yeah. Okay, I'll use filter first. So what filter does is that it's the same thing, right? It has you're passing a lot of things, right? And it will only allow you pass certain things that meet a particular condition. So in my case now, I don't want it to pass any value that is equal to x. So I'll say only pass things that are not equal to x. Yeah, then we now map. But you cannot combine everything into one with filter map. There's something called filter map. But let's just do this. So now we map, and we know that everything we're getting now is what we're looking for, right? So we have like we don't even need it. I just call it x. So we need to build a new polynomial that is like x minus this thing, right? So x minus something means that x is 1. X always has coefficient 1. And this is just the negation of the new thing, right? So I'm just creating a univariate polynomial. Oh no, I can't do this anymore. Yeah, I'll do that. But the first job is 0, 0. I know what I want to pass. Yeah.
Sorry, when you were doing
Yeah.
were you as good as this in
Valid question.
I was not as good as this.
No, not as this.
Let me see your first implementation.
If you say
Whatever
as this,
Let me see your
implementation.
implementation. Like back then, those days.
Yeah, I don't think.
Wow.
You know, it's forcing you to think about yourself.
And so these are benches, right? This is how like you can bench. Let me see.
so you're writing benches in your first degree.
This is last month.
Wait, no. This is evolving. Okay, you know what I'll do? I'll go to the file, then I'll go to the history. Yes, and then we'll see what it looked like.
Okay, you updated it.
Yes, always auditing is finding better ways. So in multilinear univariate. Univariate was so bad. It was so bad. So I did dense at that time. So this is what I'm about to write now. Yeah. So you guys will all have to move to field at some point because we don't use this thing. Coefficients. Why did I need this? I don't know. So this evaluates. So this is what we're doing today. This is what we did today. The reverse and then the x this thing. So we didn't know this existed. We were looking at lambda works implementation of evaluation. Then we saw this thing here. And we're like, what is this? So we had to spend like hours, just me and Francis, just banging our head at trying to understand what this is. Then we now figured out that, they are reducing the amount of multiplications that they are doing by using this distributive property. So that's how we knew that was possible. So interpolate now. I just have an interpolate that has just y's. Right, no x's. So I have another one here that has both x and y. So when I'm interpolating just y's, I now I put a 0. What's this?
Oh God.
It's so bad. Okay, no, we can't field elements.
I'm
Okay.
multiplying the y by
Your condition.
the x.
That's a sign of growth now. That's a sign of growth. Even this self is bad. Hmm? 1 month.
This was last month.
No, this was not last one. This was 6 months ago. This was 6 months ago. So see, I didn't create a function for the Lagrange. I had to
Is this part?
this dense. Where do you see monomial?
Plus sounds cool.
74.
And this line 78.
And it's just a variable. Then I'm just adding it to each other. Yeah, multiplicative identity. This is a polynomial that if you multiply it with any other polynomial, you get the same polynomial. You know the same way you can do like one is the multiplicative identity.
Yeah.
So 1 times anything is always that thing. So you can have the same idea for a polynomial. That when you multiply with any other thing, you'll still get back that thing, which is just constant 1. Polynomial that has constant 1. Then you guys come and do multilinear polynomial. This one is really interesting. Like this one is really good. Well, I'm supposed to be showing. I'm gonna make my repo private. I'm gonna make it private. Before you go. Hey. Don't deceive yourself. Okay, so yeah, let's continue the basis. So exactly. To what end? What are we doing now? We're trying to create the x minus distinct polynomial, right? So we're doing univariate polynomial new, right? And then it's now a vec of constant is what? Minus x, and coefficient of x is 1. Right? Why is it not FM thing? Okay. Yeah? So now we just collect. We collect the univariate polynomials. Okay? How am I doing wrong? How am I doing wrong? Why not? Why not? Oh, Vec, I'm so dumb. Okay, so now we have all our numerators, right? So how about the things at the top? And to get the thing at the bottom, all you do is you evaluate each one at 1. I don't know if you guys remember. So, if we wanted to create something that looks for 2, in this case, right, we'll do x minus 1, x minus 3. Then we're technically like evaluating the top one at 2. So 2 minus 1, 2 minus 3. That's technically what we're doing. So another thing I just realized that we can actually just multiply it. Then we can multiply it, then evaluate the multiplied thing at 2, rather than evaluating each one. But multiplying is not going to be nice though.
But before we go to the numerator, could you please explain this?
Okay. Yes.
Especially that minus x
And
part.
1.
Yes.
Oh, the minus x and 1. Okay. So, this is a polynomial, right? The constant is this one is a constant, right? And this one is x raised to the power of 1 and x raised to the power of 2. These are our dense representations. So what we'll put here is the coefficient of x, and what we'll put here is a constant. So what are we trying to do? Let's say our x is 1. We are technically trying to do x minus 1, right? This is what we're trying to create. So the constant is minus 1, technically, right? Because this can also be written as x plus minus 1. So this is the polynomial. So our constant is minus 1. And minus 1 is what we call x here. Because we're mapping the interpolating sets. So we need to put minus 1 as the constant, or minus whatever as the constant. Mitch?
Yeah?
Were you asking? Want to ask a question? Okay. So that's why I put minus x as the constant. I think the wording of the x might have been the problem. So instead of this, I could just call it like I don't know what to call it. What's n? What's n for? But just know that this is coming from the interpolating set, not necessarily x as a variable or anything. Does that make sense? Then it's now like we have something that has x in it, but the coefficient of that thing is 1, right? So then it's x minus 1. What's the coefficient of x? 1. So that's why I had the 1 there. You don't get it? Okay. Okay, how would you represent this? 2x. Dense. No, you. 0, 2. 0 as a constant. Why 2 here? Why is this 2? Coefficient of what?
X raised to power 1.
X raised to power 1. So in this case, what is the coefficient of what is the coefficient of x raised to power 1 here? So that's why we represent this as minus 1 and 1.
Yeah.
So the 1 is the coefficient of x.
But where is the x minus 1?
Where's the x? So x minus 1 is from Lagrange. You know that L function that we have been creating. So we are doing x minus. So let's say we wanted to do interpolated set of 1, 2, 3. I wanted to create an L function that can find 2, right? So to create this, we'll do the numerator is going to be x minus 1 and x minus 3. Then we now divide that by
2 minus 1.
exactly. So what I'm trying to build now is this top part, right? Okay. So what I'm trying to build is the top part. So what I'm doing, that's what we're doing here. So we're going over the interpolating set, which is this 1, 2, 3. So we're going to build an iterator that is going to sequence out 1, 2, 3, right? So 1, 2, 3 has been turned into an iterator. Then the next thing we need to do is, remember that we're not doing x minus 2, right? It's just x minus 1 and x minus 3. So we have to filter. So the filter will not let something pass if the condition is not met. And what is my condition? The thing must not be equal to, in this case 2, yes. So that means it's only allow 1 and 3 to pass. So the filter result will be something like this, right? Then now we're going to map, okay? So map is now going to just see 1 and 3. So what I'm trying to build now is I'm trying to build x minus 1 and x minus 3. So I'm trying to build 2 new univariate polynomials. X minus 1, x minus 3. You get? Yes.
So in this case, okay, you're still going to build for the...
So I need to build for them. So this minus this 1 here is what we're calling xn, right? But I need to negate it, right? You know, we're subtracting it. So that's why I have minus xn, okay? And then x is always 1, regardless of the 10, right? So it's just 1.0. So this here represents x minus something. That something is xn. Do you get? Makes sense?
Make it 0.
Yes, because we want to make it 0 at the top. But we filter
So
out.
the 1 is the coefficient of x plus 1.
Yes, it's always the coefficient of x plus 1.
So please, can you go to where you created the new function?
Which new function? Oh, the coefficient.
Yes.
I just... Have you seen it?
Yes. So why are you not using the univariate coefficient directly and have to create the new one?
Why am I not using the what?
The univariate structure you created before directly and have to create a new function.
Yeah, I was just tired of typing the brackets and the coefficients. Like, you know, see the way I was doing it before? I was doing like this, like this.
Yeah.
I was tired of typing this, and this, right? So it's just easier to do. I'm just tired. Makes sense?
Yes, yes.
So now we have the numerators. What I wanted to do, I wanted to multiply them. But I feel like I need to implement prod. And I don't know how to implement prod. Product, sorry. This will shout, right? Because I don't have products. So you know, since we have already implemented, product will take an iterator and multiply everything in that iterator. So if we have 1, 2, 3, product will do 1 times 2 times 3.
Okay.
And you know,
So use the multiplication.
yes, I want to use the multiplication inside the prod, but I've never implemented. I don't think I've implemented prod before, so I don't know what the signature is going to look like. So once we implement prod, we can implement sum instantly. So implement product for. But see now, what is it giving me? It's giving me an iter. So I need to do like the result is going to be 1, right? The multiplicative identity, right? Like I can't make it 0, right? Because anything times 0 will always be 0. So I want a new univariate polynomial that it just has a constant of 1, right? Because anything times 1 is going to be that thing. Then I'm going to iterate over, for poly in iter, I'm now going to multiply and assign back into the result, right? So the result is going to be equal to the result times the poly. Then I'll return the results. So this should be products. Hopefully. Does it make sense?
I'm still confused.
Why are we doing it? I'll show you now.
You have a multiplier.
Yeah.
What's the difference between a product?
It's just nicer to write dot product. After so if I wanted to do what you're suggesting, right? I'll need to now loop over, right? And set the result and all these things. But since I'm already using this pipelining structure, I can just put the product at the end and I should be good. Does it make sense?
What is this product taking?
So product takes an iterator. An iterator here. I'm now taking each element in the iterator and I'm multiplying it by itself. So yes. So you know the numerator, we got each x minus this, x minus this, x minus this. So and the goal is to multiply everything. So that's what I'm doing here. The product. Yeah?
So 2 o'clock seems far.
To be honest, I swear.
I wanted to ask that too, but but this iterator now that you are multiplying, like can you scroll down? Okay, yes, I remember now. So I'm noticing that for every, like almost like for every action that you want to perform,
For every
you are writing, like for everything you want to do, like for every action you want to perform, you are not using like the standard or what Rust is providing. You are writing your, like for example now multiplication, you are writing your own multiply. Addition, even addition, you are writing your own addition, add and stuff like that.
The reason is that Ross doesn't know what polynomials are. Like that was something we created ourselves. So Ross does not know how to add polynomials in sparse or dense or whatever. So that's why I have to implement my own like addition. You get? Because it's a different type. Yeah, that's what I'm concerned with.
Please, can you go over this product thing?
Okay. So it's an iterator. So in the iterator, I know that each element there is a polynomial, right? X minus something, X minus.
But the collect from the interpolation stuff, if it has a vector or is it a tuple?
I've removed it now because of I'm no longer collecting an array. I'm just going to get one value. Yes. So instead of calling it numerator, I'm supposed to call it numerator. But now this map is going to return each univariate poly. So product is just doing that. Don't worry. We'll soon be done. Yeah?
So how will the program now know, like, because I said that even after defining more a multiplication function, you don't use that name more, you still use the multiplication sign. So how does it know that?
So that's why so you can see this mul. Mul is a trait given to you by Ross. So Ross says that when it sees something times something, it will check the type of the thing that you're trying to multiply. Then to go and check your code, the code that you have written for that type, and see if you implemented mul for that type. If you did, then to call that your mul implementation. If you didn't, then to throw an error. Does it make sense? Okay, let's just finish this. Let's just finish it quickly. So now we have the numerator, right? Which should be a single polynomial, hopefully.
Well, you were trying to explain the product.
Okay. So the product. Yeah, so the product is taking an iterator. The iterator in this case is going to be the univariate polynomials. So what I did was I created a new result, which is a univariate polynomial that has just a constant 1 in it, right? So that I can multiply into it. I don't know if that makes sense. So like if I want to multiply 2, 3, and 4, I'll set a result value to be 1. Then I'll do 1 times 2, I'll store it there, then the result. So it's just an accumulator. Then I'm just iterating over the iterator. So this will be giving me each of the poly from the iterator. Then I'm just doing result times poly and storing it back in here. I could have used, I couldn't have used. Yeah, I couldn't have. Because I didn't implement small assign for polynomials. Yes. Then I store it in the result. So at the end of the day, I'll be done and I'll just return the result.
So we wanted to use that.
This is
This is
our
bell.
cue to go into that mode. To go use that mode that you already defined.
So
What about key?
Wait, sorry.
with the way with the way you've implemented this, that means one can actually like think of all the possible things that people could do in
Yes, it's your type.
a univariate polynomial, add it here and make it a crate.
Technically, yes. But so there's Aquox now. Aquox is a library that has done something you're talking about.
And we have our own aqua.
Yeah, you can do your own Aquox if you want. You can do your own Aquox if you want. So does this make sense? Someone tell that question.
Yeah, you wanted to give this what it does the I don't know the iterator you know that one that we're doing the iterator.
Like you can do like the fold or you can do the reduce. Yeah. I just did this side because it's simpler.
Travis, can you do that dot fold in that playground?
Can we do? Let's just finish this thing first, right? Then we'll come back because people are getting tired.
No, no,
Huh? So now we have the numerator, right? Which should be a polynomial. Okay. So what's next? We need to get the denominator. How do we even do this? Don't we need to divide? How did you guys not divide?
Divide what? Polynomial.
If
The
the
denominator is a scalar. So you just do 1 over the denominator, then use
Scalar.
scalar multiplication.
Okay. If you do that in field, that's inverse in field arithmetic, which is expensive like mad. What else concern? I cannot just do divided by.
You can't just do slash.
Why
No.
divided by?
This is the number.
It's not a number. Numerator is a polynomial.
No.
And denominator, I will get it.
It's a number.
Yeah, denominator is a number.
So you can't just do slash. That's why
Called polynomial slash number.
No, like
That way you're suggesting.
Not
Right?
polynomial.
can
You
get
y.
the why exactly? Why
Okay,
are
so
divided by?
you y slash number, then you now multiply that whatever. Polynomial.
I know what you mean. But that will not mean that you need to return out the y. Because of the way I'm doing it.
Yeah, we didn't do this.
Yeah. I'll do the scalar more. I'll do scalar more. Yeah. So let's do the denominator. Denominator is just the wow. That's nice. That's so nice. But why is it not think as a polynomial? Why? It's not suggesting to me that I can call evaluate on this. That's weird. So does this break? Does it build? It doesn't build. How do you know the type? That's weird though. It seems like that works, huh? Does my evaluate take... So this is not needed. I could take a slice. It doesn't matter, it's just a number. Okay, so now we have our denominator. And it builds. So we have our numerator, then we multiplied it, then we just evaluated at that, and then that's what we have under. So now all we need to do is just, divide, but divide via scalar more, right? So what we do is we invert the denominator, which will be 1.0 divided by this. Then our Lagrange basis polynomial will just be like the numerator dot scalar more the denominator. And then, so scalar more I use reference, I'm not serious. Right? And then that is the basis. So now that we have the basis, we go back to our interpolate. And then it's now times y, right? And then we sum. So the only thing we have not done is sum. We're not done. Oh, I know the alpha. Yeah. What if we now test it and it doesn't work? Yeah, let's go on. So now I'm doing the additive identity, right? Which is 0. So you can add to 0 and it won't change your.
Sorry, Professor. Sorry, the sum and the add, are they not the same thing? I'm confused.
Yes, they are. They are. But this sum is specific for an iterator. So if I have an iterator of polynomials, I can just call dot sum and it will help me add them. So that's what I'm trying to implement. I'm trying to tell Rust how it should handle certain situations like that. But I'm going to be using the add that I've already implemented. You get? So for every listing in iter, then results equals result. I've not done add assign, that's why I couldn't do that. Plus poly. Right? Then return result. So technically we should be done. But I don't know if it's going to work. So do we have a test? Does anyone have like a series of points already that I can just like
Let's find for f of x equals 2x.
f of x equals 2x?
2x, yes. So we can do 2, 4, 4, 8.
Wait, so f of x equals 2x, right?
Yes.
So the points are what?
2, 4,
Mm-hmm.
4, 8.
Alright then. Right?
Yes, 4, 8.
So we need to do univariate poly. So Jude. So this is what I was talking about. You cannot do univariate poly dot interpolate. Like you don't need a specific class. So my x is 2, right?
2, 4.
How am I passing x's? This thing doesn't work out. It's so sad. Oh, it's so sad. Right? So we'll now get a new polynomial. So this is supposed to be equal to let me just get the coefficients of what?
0 and 2.
So constant is 0.
Silence before
Why is it 2?
God have
It's 2x. The original polynomial was 2x.
Okay.
Well,
God have been.
I don't want to run this thing.
No, you expect it to not.
Yeah, we expect it to be
Expect.
work.
You expect it to be.
Expect it to fail, so we want to.
Thank you,
Makes sense.
Yes, it's waiting to play.
Yeah, let's go.
That's 2.1.
Yeah,
Nice one.
So but this is slow.
very strong.
Thank God for that.
There's a much faster way to do Lagrange interpolation. So this is running in O of n square.
Yeah.
There's a way to do it in O of n. Yes.
So
The
the
rest-
entire
The entire Lagrange
not
in
just
O of
the
n.
mall or the add.
No. Lagrange itself.
Like a different algorithm.
Yes, a different algorithm. We won't go over it now because everybody is tired. But
Can we get to
Can you share like the material or something?
yeah. Is this like proofs, arguments, and zero knowledge?
Oh.
Are you
Let's see
serious?
the chapter.
Like this?
Yeah.
Because the chapter. So that will
Yeah, sure. So let's stop here. Come back by 2. Yes.
We should rest now.
Rest now and come back by 2.
Alright, no.
That's like 49 minutes. So that should be good.
can we get
Then 2 to 3.
2 to 3.
Yeah. Something short. Yeah.
Something like
An application.
we can have. Okay. Thank God for that.
You're saying what? The code and the video too. Eventually. But the code. I'll send the code.